Structural Engineering Forum of India, in association with VJTI Alumni Association and VJTI Structural Engineering Department, has organized this one-day seminar. So within a few seconds, chief guest of the today's function, Director VJTI, Dr. Sachin Kore, he will arrive and we will start the program. Yeah. So I request all the dignitaries to come on dais, please. Professor Rupen Goswami, Professor IIT Madras, Professor Jaswant Narlekar, renowned consultant and speaker of the today's function, Dr. Sachin Kore, Director VJTI, Engineer Ms. Alpa Seth, MD VMS consultant and from SEFI, Engineer Umesh Doshi, Chairman VJTI Alumni Association, Engineer Shantilal Jain, President ISSE, Engineer Hemant Vadalkar, Honorary Secretary ISSE. Indeed, it's a great day because all these renowned organizations has, with the motto of dissipation of the knowledge to the professionals and young engineers, also young budding engineers, they have organized this beautiful one-day workshop on the relevant topic of the civil engineers and structural engineers. To begin with the program, any program, technical program and educational program, we begin with the lighting of Holy Lamp. So I request chief guest of the today's function, Dr. Sachin Koreji, to join here for lighting of the lamp. It is symbolically we are doing this.
हेलो किधर है बेटा तू ज़्यादा हॉल है ना यहाँ पे जल्दी हो जाए कार्यक्रम चालू हो गया अरे तू भी डाल
Thank you very much, sir. So this workshop is review of proposed changes in IS 1893 Part 1, that is criteria for earthquake resistant design of structures, IS 456 plain and reinforced concrete code of practice, IS 13935 seismic evaluation, repairs, strengthening of masonry buildings guidelines, and IS 16700 criteria for structural safety of tall concrete buildings. So this is the technical bonanza for the professionals and young civil engineers and structural engineers. On behalf of all these organizations and our technological partner, Messrs. Ultratech Cement, I welcome all the dignitaries and speakers and office bearers of all these organizations. To formally begin with the function, I call upon Engineer Shantilal Jain, President of ISSE, to welcome all the dignitaries and the audience.
Good morning. On behalf of Indian Society of Structural Engineers, SEFI, VJTI Alumni Association, I welcome Director VJTI Dr. Sachin Kore, Professor Rupen Goswami. He had traveled all around from Chennai. Today for AME started from his home and he is here with us.
Hello.
Umesh Doshi, Anil Iraji, and all my young and future engineers.
Hello.
We are all here to celebrate 25 years of ISSE. ISSE is working for civil engineers and have presence all over India and continuously do activities for all of us. And so I welcome all of you once again, and time is short, we will move forward.
Thank you, Shanti Bhaiji. Now, with the words, we welcome all the dignitaries by offering flowers as a token of our love and affection. I request Shantilal Jainji to welcome Professor Rupesh Goswami, the speaker, with the bouquet. I also request Shantilalji to welcome Engineer Jaswant Arlekar, another speaker of the today's workshop. I request Shantilalji to welcome our Chief Guest, Dr. Sachin Koreji, Director VJTI. I request Honorary Secretary Mr. Hemant Wadalkar to welcome Ms. Alpa Seth. I request Hemantji to welcome Chairman of VJTI Alumni Association, Mr. Umesh Doshi sir.
हेलो. हाँ बोल जल्दी आ रहा अंदर बेटा. हाँ हाँ जल्दी आ अंदर आ. हेलो. हाँ 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 अंदर आप.
I request Dr. Sarode sir to offer a bouquet and welcome President ISSE Shantilal Jainji.
हाँ लाइक ना मी लोक आलो.
I request Mr. Pandyaji from Ultratech to welcome Honorary Secretary Hemant Wadalkar. Also, our technological partner, Ultratech Cement. So, I welcome Engineer Satyaki Sarkar, All India Technical Head of Ultratech Cement. So, in his absence, I request Hemantji to welcome Mr. Pandyaji, Regional Head, Ultratech Cement, with the flower of bouquet. Thank you all for patience watching. Now I request Honorary Secretary Mr. Hemant Wadalkar to give brief about the journey of ISSE.
dignitaries on the dais. Director VJTI, Dr. Kore sir, President ISSE, Shantilaji Jain.
Hello.
Our guest speaker, Dr. Rupen Goswami, who has come all the way from IIT Madras. Ms. Alpa Seth, Jaswant Adlekar, Doshi sir, Anil Hira sir, all my colleagues and civil and structural engineers friends. We are very much happy today to celebrate 25 years of ISSE. So I will just take you through the brief journey of ISSE, what has happened and how this organization has been formed and so on in a very brief manner. And we must express our gratitude to all the persons who supported ISSE wholeheartedly during its journey in various forms by giving their time, energy, money and all such things. So as you know, we are celebrating Silver Jubilee for ISSE. So that's why this grand function has been arranged. And the problem that are faced by structural and civil engineers, mainly the codes. So that's why we have invited experts to talk on this subject today. So that we'll be hearing during the course. And as I said, ISSE has just completed 25 years yesterday. The organization which is dedicated to structural engineering was formed by eminent structural engineer, late Mr. R.L. Nene, with 10 advisory trustees, and this has been registered as a public on 9th July 1998. Formal inauguration was done on 29th January 1999, and that's how we completed 25 years yesterday. Now all civil engineers are welcome, so we encourage all civil engineers to join, though this organization has started as a forum for only structural engineers to begin with, but now it encompasses all civil engineering fields, and we welcome all civil engineers now. So on this occasion, we must salute the great visionary, late engineer R.L. Nene, who was the founder of ISSE, eminent structural engineer, and he has done at that time the manual of practice, which is very popular among all the structural engineers, which is available in our publications, and this is a leading light for ISSE. So we must remember this visionary leader. Now, as I said, I will just briefly introduce all the members. Let me start. Nene is the founder. A.G. Dharmadhikari, unfortunately, he is traveling and is not able to attend today's function, but he is one of the founder members, past president of ISSE. He has arranged many lectures and functions for ISSE. Devoted personality and lot of dedication he had for ISSE. So he is still working with us and guiding us. Late Mr. S.G. Patil, he was also past president of ISSE. Late Mr. M.C. Bhide, he is known as a bridge expert, bridge engineer, who is also one of the founder member of ISSE. He has arranged many lectures and workshops on bridge engineering and bridges. So we must remember all these personalities. Late Professor M.D. Mule, he was our professor also in VJTI. So we learned structural engineering from Professor Mule. So he is also he has conducted many lectures and seminars and lectures for ISSE. Late Mr. G.C.O., he is remembered for giving the shape to our ISSE journal or publication. You can remember, so we are in 25th year and continuously we are publishing this technical bulletin, that is quarterly, without any break. So he started with Mr. G.C.O., he has taken it to the new height. J.R. Raval, he is sitting here, he is with us. He has also conducted many functions for ISSE. He is also one of the founder members. P.P. Dandekar is a past secretary He is also traveling to US, so he couldn't attend the function. But we must remember these people. K.L. Savla, past secretary, is also with us here. Mr. M.V. Sant, he was also past joint treasurer and membership verification. So he has handled all the membership requirements and the form scrutiny and all these things. So he helped a lot in that. He is also not keeping well, so also he couldn't come to the function. Sachin Joshi, he is now a big person, big name in the bridge engineering. So he has developed this software now for recording all the bridge structures data into the software. So he is also one of the members from ISSE, initial founding members. Mr. Umesh Harvelkar, he is also very much helpful and he is also conducting a lot of functions for us. He was also editor of ISSE for a few years and he also conducted many seminars for civil engineers. Late Professor D.S. Joshi, he was also past president of ISSE and he has written a very good informative book on RCC design based on the earthquake resistance structures. So this book is also very, very popular, published by ISSE, and a lot of people are still referring this book. So it's a great contribution for us. Late Professor G.B. Chowdhury, he was also our past president. He was also very much instrumental in arranging many lectures. He was a geotechnical expert and he was also our professor at VJTI. So he taught us geotechnical engineering. Mansi Nandgaonkar, he is very much here. And she handled all the finances and kept our money safe. So she is a treasurer for a long time and still continuing to help us. The important part I must tell, in the society bylaws, structural audit was necessary, but initially the word architect has been inserted. Now she has fought for that and changed it to structural engineer, because structural audit cannot be done by the architect. So that has changed because of her. Shadraji Jain, as you know, the dynamic president of ISSE. He has taken ISSE to very new heights by opening many local centers and student chapters, and lot of growth of membership has happened during the tenure of Mr. Shantilal Jain. So we must appreciate that. Myself, I am presently secretary of ISSE, devoting some time for the work for ISSE. And I am also editor for ISSE Journal. I am trying to take out the journal for last 10 years. I am handling the activity for taking out the ISSE Journal. Late Mr. N.K. Bhattacharya, he was also our advisory trustee. He was also editor of ISSE Journal for a few years. And he has also arranged some technical lectures for ISSE. Madhav Chikodi, he is also arranging technical lectures for student chapters of ISSE. Ranganath Satam, he is also very much here with us. He is also coordinating many seminars and functions for ISSE. Paresh Ungarkar, he is also coordinator for many functions of ISSE. And he is also giving lectures on green concrete. He himself is a technologist. Vatsal Gokani, recently we have published one book written by Vatsal Gokani, which talks about performance-based design, which is the future for all these designers now. Now I must appreciate our supporters who always help ISSE by sponsoring the functions, by giving donations. The first donation was given by B.G. Shirke during the first inauguration session in 29 January 1999. So at that time he donated 1 lakh rupees and then ISSE has started from that day. So I am going to acknowledge all this. Tata Steel, Ultratech Cement of course is with us. They are sponsoring a lot of our functions. Tata Structura, Krishna Conchem, Tata Tiscon, Samrachana, R&M Rasayana, ArcelorMittal, RWDI, Stat Engineers, Rufex, Gamzen Plus, Autocompo. So these are all our supporters. They have given advertisements at our journals. They supported our events and functions. So we must acknowledge their contribution. Now I am not going to all the details. Everyone knows about that. What are the aims and objectives of ISSE? So basically, it is guiding all the structural and civil engineers. Define the boundaries of responsibility for structural engineers, commensurate with the remuneration, and to get deserving recognition in the society, lies with all the government organizations, assist in coordinating and forming the certification policies. Now you know the new development control regulations has come. So ISSE played very important role in ratifying the certification formats. Earlier, if you remember, corporations always want that everything is responsibility of structural engineer. So they just take it in writing that okay, whatever happens, I am responsible. That is not the case. National Building Code gives the guideline. Structural engineer is responsible only for the structural design. Site supervisor is responsible for day-to-day work at site, checking the quality of material and so on. So these formats have been developed and ratified in the Unified Development Control Code due to lot of efforts of ISSE, Pune Center and Mumbai Center jointly, and that's how this new format has come into picture. So ISSE is doing work in that direction. So this is all I am saying to apprise all the state government, semi-government bodies and all. Of course, again to update the members on the latest developments in various fields. That's how we arrange a lot of functions like seminars and workshops. We call upon the experts to disseminate the knowledge and update all our members in the latest practices. So that is one of the main objectives we are trying to fulfill. What are the main areas of focus for ISSE? It is not only structural engineering, but of course anything related to civil engineering nowadays. So it started with, of course, structural engineering, designing and detailing is the most important part, no doubt on that. Computer software is one of the areas where also we focus. We have conducted many workshops and seminars on this subject as well. Material technology and new materials. Of course, teaching, research and development is a continuous process. We keep learning all the time, and that should happen. Rehabilitation of the structures is another main important area where you need to again assess the structure, audit the structure, and then do the rehabilitation of the structure. Sometimes you have to strengthen it based on the latest code of practices. So that is retrofitting also is required. So that is another big area. Concern technology and management, of course, new material, new construction practices are coming up. So we have to focus on that. Geotechnical and foundation engineering is one of the key areas. Environmental engineering nowadays, that is again most important. Non-destructive testing again is a big subject by itself. That comes under all these audits and inspection of structures. Then re-engineering. So we touch upon these aspects also. So these are general focus areas for ISSE. We try to address. This is a present committee of ISSE who is holding the office at headquarters in Mumbai. And of course we have different centers, local centers also at different locations. So just to sum up, it is at Pune we have our very dynamic and active local center. They are also conducting a lot of functions. They are helping our main office and our members in a lot of activities of ISSE. Solapur, Aurangabad, Kolhapur, Navi Mumbai also we have center. Palghar, Baramati, Amaravati, and recently we have started Kalyan Dombivli also last year. We have different student chapters, so of course there has to be interaction with students. So that's how we try to open student chapters and try to interact with professors, students. So these are some of the student chapters we have. And VJTI also, we already have the center, but formally we will be distributing the certificates to students after this function in the evening. We have different type of memberships available. Like we have the live member, we have corporate members, we have junior members and the student members. So total strength as of today stands more than 3,000 members we have. And I appeal, those who are not our members, please become our member, strengthen our hands. We have different publications. What are journals we have? So we have quarterly publications for our journals with all the technical articles, sharing of knowledge as I said. So we again appeal to all our members to share your knowledge and experience with us so that we can just share it with our fraternity. So it is a platform for knowledge sharing as we call it. So proceedings of seminars we have taken out in a form of publications and bulletins. Those are available. This is on our website, you can just refer to that. Here are some of the glimpses I just wanted to show. Some of the publications. And of course, we have many resource persons and speakers we invite for our seminars and workshops. So I thought we must acknowledge all the contributions. But the list is too long, so I am not going to read all the names, but I will just try to project that. So about 70-80 people, they have contributed as our resource persons and speakers for different workshops and seminars at ISSE during all these years. So all the prominent personalities are with us. So I am not going to read the name anyway, but these are the people we must acknowledge their contribution as our speakers. It's a long list. I will just run through that. Similarly, we are trying to take out the quarterly journal without any interruption, and we are again appealing all the members, all the experts to share their experience and knowledge so that we can publish it in the form of technical literature. So again, I have made a list of all the contributors as authors to our technical publications and journals. So that is also a very long list. I will just try to project that. One name I must mention here, Dr. N. Subramaniam. Presently he is based in US, but he is writing a series of articles for us, James of Structural Engineering. For last 10 years, he is writing the articles continuously. So we must acknowledge the contribution of Dr. N. Subramaniam. And of course there are many other stalwarts in the field like Dr. Nori, Shirish Patel, Kamal Adkar Sahab. I am not going to read the names again, but these are all contributors to our technical journal as well. So I will just run through the list. Again, about more than 100 authors are there, those who have contributed for our technical bulletin. Again, I appeal to all our engineer friends, whatever contribution you can have, you can share with us. Because in every side, every project tells us something new, something different. We have a good website, www.issse.org.in. So we have all the list of publications available on our website. All our technical journals are also posted there at the website. So you can just have a look at our website. And good technical references are also given there. So we conduct a lot of events for professionals and students. So there are lectures, seminars, workshops. We arrange some site visits also for the students. And of course interaction with professionals, academia, and suggest some research topic also. Because what industry wants basically, that needs to be again research during your MTech and doctorate levels. So then our industry will benefit from this. So these are some of the just glimpses I am trying to show you. Dr. Siva Murthy was the guest for MIT student chapter. This is a workshop for wind engineering by Dr. Suresh Kumar of RWDI that we conducted. So we arranged one site visit for Statue of Unity also. This is some lecture of structural audit. So I will just run through that. So various functions at various levels by our local centers as well. There are some student chapter photographs. So we have a student chapter at Aditya Engineering College, Andhra Pradesh also. And I must mention here, during the COVID time, we couldn't really conduct any physical program or lectures. So at that time, we have done all the online functions for the students and professionals. So seminars were continuously on, but in the form of webinars. So that also was there during the COVID period. So the main focus, as I said, the role and responsibilities of structural engineers to be defined. Structural audit, these are the main focus areas. ISSE is looking into professional ethics and follow with the government organizations. So as I say, again, this is a platform for social work as I look at it. So keep learning and share your knowledge with our fraternity. Spare some time for our fraternity. Join hands to make our structure durable and sustainable. That is, I think, the most important part we must keep in mind, which will of course help our building the nation. So again, once again I appeal, this is again giving back to society. So become our member and support ISSE. So here again I must mention, we are appealing for donation to ISSE, because after 25 years we still don't have our own office. So our aim is to collect some fund about 1 crore rupees to get our office, because right now we are operating from Dharmadika's office till right now it is from Mansi Nangav's office we are operating. So the aim is to have our own office. So Mansi Nangav has started the donation. She has donated 25,000 for ISSE. Similarly, K. Savla, he has also donated 25,000 rupees for ISSE. So today morning I got a message from RC Tipnis. He is willing to donate 50,000 rupees for ISSE. So we have just started, and I also from my side announced to donate 1 lakh rupees for ISSE. So please come forward, please help us, become our member. So let us come together and have a strong ISSE. Thank you very much.
Thank you, Mr. Hemant, for sharing the glimpses of ISSE and showcasing what the activities they are performing for the fraternity. Thank you very much. Now, going further, we would like to felicitate our another speaker. He is a leading structural engineering consultant, world famous expert in tall building and complex structures, and he did many complex projects in abroad also. So I welcome Anil Hiraji, and I request Atilanji to offer a bouquet and welcome Mr. Anil Hira. Now, as Honorary Secretary, Mr. Hemant has told that there is remarkable contribution of the many stalwarts who brought this ISSE journey up to this stage, and successfully they have completed 25 years, that is Silver Jubilee they are celebrating, and yesterday was the anniversary of ISSE. So big compliments to them. So on this occasion, we would like to express our gratitude to our senior most members of ISSE. So I request Engineer K. Savla sir to come on dais, and I request Dr. Sachin Kore, Director VJTI, to welcome him and felicitate him for his outstanding contribution to ISSE. There is another senior member of ISSE who did many technical programs, and he is a familiar face for VJTIs because we are sitting in this auditorium, and he is a ex-professor of VJTI. So I request J.R. Savla sir Rawal sir to come on dais, and I request our director to felicitate J.R. Rawal sir. And I am very happy to share that I am student of Professor Rawal sir. Now I request Chief Guest Dr. Sachin Koreji to address the gathering, please.
A very good morning. First of all, apologies for the delay. and I'm very thankful to Indian Society of Structural Engineers as well as the Structural Engineering Forum of India and VJTI Alumni Association for organizing this particular workshop and giving me this unique opportunity to be a chief guest in VJTI. I am very thankful to organizers, Engineer Shantilal Jainji, Engineer Hemant Vadalkar, Engineer Alpa Seth, Engineer Rohit Pandya, and our Mr. Umesh Doshiji from Alumni Association for organizing this particular event and discussing on the preview of proposed changes in IS 1893. I'm very humbled to be chief guest here in front when the speakers are like Professor C.V.R. Murthy, who is a mentor, professor from IIT Madras, and also Professor Rupen Goswami from IIT Madras. So this is very nice to see that professors from IIT Madras will be advising us. And I'm also very happy during the panel discussion, Engineer Alpa Seth and Engineer Anil Hira, they will interact with you on the various topics. So that's a unique opportunity for all of us. I take this opportunity to tell you about VJTI. VJTI, since its inception in 1887, remained the first choice for top performing students in Maharashtra. Till today, we get students who score 99 and above in their CET score. So that's what we get cream from the Maharashtra state. VJTI moved, we are celebrating centenary year on this particular campus, that's Matunga. We are celebrating 100 years, so the building in which we are sitting is 100 years old. It's 1923 when we moved to Matunga campus here. Civil Engineering Department started in 1912 and VJTI Structural Engineering Department started in 1960. VJTI is playing a very important role in structural health monitoring services for the entire Maharashtra state and particularly in Mumbai region. And I'm very happy that our professors like Professor Sangre, Professor Bombole and other faculty members from the department, they are contributing significantly in this area. I must tell you that recently VJTI received rupees 5 crore grant from Government of Maharashtra for Center of Excellence in AI and ML. I'll be very happy, though I am not an expert in civil engineering or structural health monitoring, but I'll be very happy if we can connect such dots and develop a collaborative efforts like can AI ML with thermography imaging technique combined with real-time monitoring. I don't know, I'm just asking a vague possibility. Can be a real structural health monitoring, which is a need of an hour, be in place. At the same time, can non-destructive evaluation combined with machine learning images, can they predict the life of the buildings? And we will be very open to such kind of collaborations. At the same time, I must tell you that VJTI also received rupees 10 crore grant from Government of India for setting up Center of Excellence in Textile Department. And we will also be very happy, the one major theme is geotextiles, is the area in which we will be working. We will also be very happy to extend our collaborations, possible efforts in strengthening these particular activities. Looking at the topic of today's discussion, I'm not expert to comment on, but as a user or as a common man, I can definitely say experiences during the childhood when somebody heard about Killari, and when I spent my 10 years in Guwahati, which is also in an earthquake zone. And how does it feel in the midnight when you have to come out of your house with the entire family and evacuate the building, and how stressful that is, that I know very well. So it's a very important and big role as an engineer, as a structural engineer, as a civil engineer, one can play to save number of lives and to also give sufficient information to the occupants and save various lives. So I think, as I said, we started late with the program. Apologies for that. So I'll keep my speech short. With this, I wish you a great success for this particular workshop, and again I welcome you to VJTI. Have a happy stay and a successful workshop. Thank you very much.
Thank you, Dr. Kore sir, for your nice words and giving assurance to have the collaborative efforts for the betterment of society. So, thank you very much. And now, I declare that inauguration ceremony is over. We'll have a short break and then we will immediately start the technical lectures. So, I request dignitaries to... Yeah. So I request all the dignitaries to have a seat in the front row. And we will immediately start with the technical sessions. There is one appeal. All the delegates has provided with the kits and writing pad is also there. So if anybody has got any doubt, any questions, they can very well write on their writing pad and pass on that sheet to organizers. So all your queries will be answered. Are in seismic design of reinforced concrete and steel structures. He has co-authored numerous publications with Professor Murthy, such as Earthquake Behavior of Buildings and Introduction of Earthquake Protection of Non-Structural Elements in the Buildings. So with a very short and crisp introduction, I request Goswami sir to begin with the lecture.
A very good morning to all of you. The voice is a little choked, but I hope it's okay and you will be able to bear with me. First of all, I mean, it's an honor to be here and in this institute, of course, and I see a lot of senior people here. I sincerely thank you all for taking time on a working day and be here for this. It just shows that not just we, some of us, but all of us are very passionately interested about this whole topic, right? And so this is going to be an occasion for all of us to think about this whole profession that we are in, particularly with regard to two important aspects. One is, of course, we are going to talk about IS 456, and I think that is something more than the earthquake engineering course. It's the 456 which matters a lot. It's the bread and butter, roti chawal, whatever we call it, for all of us. So that excitement we will have post-lunch session. But before that, the earthquake problem that we have, let us try to understand what are the issues, main issues here, and then we would also love to, get feedback and your opinion and your suggestions on that, right? So I'm only going to present the thinking process that is currently going on, so that you can pitch in and then give your ideas also. If I had the opportunity to ask all of you even before starting anything, what is that single question that you have on 1893? 1893 part 1 and part 2 were under wide circulation some time back, so all of you have seen that. So what would that one question be? If you are allowed to ask one question, what would that question be? Well, I guess you would have some question related to the hazard part. So I'm going to start with that and talk about the hazard part. But more interestingly, what is going to happen is in future is that when we talk about earthquake-based engineering, earthquake-based design and related standards, there are a lot of standards that is practically there. As a student, it becomes difficult, and even as a practicing engineer, it becomes difficult to remember all this. So we are going to simplify the whole thing, and there is a lot of harmonization process that is underway. So we are going to talk about only 3 verticals, which is IS 1893, 13920 and 139, so that it becomes simpler, and I'll talk about the whole setup, present the setup. The first thing is, we are talking about revision of IS 1893 part 1. Now part 1, as it stands today, has 2 parts to it. One is the general provision and the things, which now is going to only stay as the general provisions for earthquake-based design. So what are the things? So the original mandate, after a lot of deliberations in BIS, was that let us simplify and harmonize our earthquake-based design codes. So as I said, when we design any new structure, we have to look at 2 components. One is the demand, which is the hazard, seismic hazard part. The other is to provide capacity for that. So the idea is to have 1893 vertical providing demands for design of all these different types of structures. And then 13920 to provide provisions and specifications so that these structures can be designed to have requisite capacity. So that is the only 2 verticals, and that is where we are going to have different parts for each of these structures. Now when we talk about existing structures, right? So there we have to do assessment, and there are 2 parts, 2 different components are required. One is, of course, the demand, for which the old structure has to be reassessed, and then the process of assessment and then coming up with strategies for repair, the decision-making process which will lead us to repair and repair. So that vertical is 139. And so if we now look at these 3, this is where we are going to put all the different types of structures, and then we'll have a standard format for it. So this is the whole agenda that DIS gave us, and based on which 1893 is now getting revised. The proposed draft was circulated, and this is what we are going to discuss right now first. What is the motivation? Of course, we have had 1893 for last 5 decades, but then we also have had surprise earthquakes in India. We have had lives lost and properties lost in many of these earthquakes. But the most interesting thing is that we have about more than 60% in fact today population living in the higher zones, higher seismic zones. And the surprise events that we have had were significantly higher than what we had originally estimated, or even today we believe these regions can provide. So as and when these different Director VJTI mentioned about Billari, so and there was Jabalpur, and starting from Koina and so on and so forth. So as and when all these earthquakes kept on occurring, we kept on updating our zone map and also the zone and the zone coefficients. And so it is a process that has been happening for many years. It's not a new process. But today, again, so in 2024, the work started a little earlier. But today again we are at a crossroad where we definitely have a need to update this once more, and that is what we are going to discuss. But the challenge in all this is that there is insufficient data really recorded data. When I say data, I mean recorded data of past earthquakes. And then because of which also there has been an underestimation of the earthquake hazard in the past. And obviously, why do we have insufficient recorded data? Because we have insufficient instruments in the country. Not every part of the country is well instrumented as we would love it to be. And I'll show you the statistics also. So, as a first cut, if you therefore look at what is the trend, right? You get to see that in reality, the peak horizontal ground acceleration that has been recorded or interpreted from different intensity measures that has happened due to real earthquakes that has happened along major similar tectonic regions, you will see that these are somewhere close to 1G. And these are all recorded data. So there's no bias in that per se, right? And obviously it fits well with the correlation that we have, generally accepted correlations. So the point is that when we say that the maximum earthquake ground acceleration can be 0.1, 0.2, 0.3, that gives us the first indication that there is a need to look deeper into the whole process, right? And then, so that is the whole idea, and that is where we thought, it was felt that we need to take seismic hazard analysis for the country in a much deeper way, and that is where the whole work began. So our design code values of 0.1 to 0.2, 0.3 did not seem okay in terms of things that have been recorded in the past. And also, our own experiences in the country, not just from other parts of the world, our own world, the country experiences tell us that there is need. So therefore, this revision is coming up, and these are the different parts of IS 1893 part 1 that is going to be there, and I'm going to focus on this item number 6, the serial number 6, which is the earthquake hazard, which is the major part. So what is the major change? The major change is in the hazard and the way the hazard is estimated. Now, what is going to happen is, you have already seen the draft, so you know that the hazard levels are different, and if you compare a certain value of Z value, for instance, you will see that there is a difference. And then the question automatically that comes to mind is, how come there is such a, so much of change? Well, it has not happened overnight. Honestly speaking, there has been a very systematic effort towards this made by various people. And if you look at these 3 documents published, with support from NDMA, this work is more than decade old. And every time there has been refinement, and I'm sure some of you, who are sitting here have been part of various committees over the years, either reviewing such work or providing inputs to such work, and so on and so forth. And so, after all these years of very rigorous study, today we are at a level where we are talking about a new seismic hazard assessment of India, where a probabilistic seismic hazard analysis has been carried out. Now, here, of course, this is not the end. There are multiple levels that can be done. I mean, those who work in this area. To begin with, we have been using isoseismals of past earthquakes to determine our zones. You saw the transition, how the seismic zone map of India changed. Those were essentially based on the isoseismals of the past events. Then one can do a deterministic analysis with mapped faults, which was also considered. And today we are at a stage of probabilistic analysis. We need more instruments, we need more instrumented data, we need ground motion prediction equations to develop based on recorded data from the Indian landmass. And finally, we have a way to particularly, even today, we are actually not considering near-fault effects, which is a significant thing that is going to happen, come up in the near future. Because India, if you see the tectonic feature of our country, we have a 25, a long thrust convergent plate boundary, and that is where these near fault effects can be significant. So we will reach there. But for the time being, how is this hazard assessment done? It is made up of two parts. One is the deterministic part and the other is the probabilistic part. I'm not going to go into the details of all this, but essentially there is a data, actual recorded data which is used, and then there is, based on that, the actual fault map is used, and then using a statistical method, this analysis is carried out. So the hazard that we are going to see is an outcome is basically a hybrid kind of a thing, where both deterministic as well as state-of-the-art probabilistic seismic hazard analysis methods are used to come up with that. What is the output? The output that we got is that we get some numbers of peak horizontal ground accelerations for certain return periods of events. So this is a new concept that we are going to see in the seismic event, right? Earlier we had only what we know as zone factor Z values, but that Z value did not come with the concept of return period. So what is this return period? The return period is essentially a statistical number, so as to say that the recurrence of such size of earthquake is so many years. Now it does not mean, for instance, if we talk about an earthquake of 2,475 years, it does not mean that that earthquake will occur only after 2,400 years. It can happen right now, it can happen tomorrow, or it may not even happen, right? So that is the thing that we must keep in mind. Now the question is, why this number, magic number of 2475, 975 and all this? We will see why it comes in this particular fashion. Essentially, when we design, we always take risk, consider some probability of that particular level of demand to be exceeded, what we call as probability of exceedance. So essentially, if we consider a regular structure, a normal structure to have a design life of 50 years, and then if we want to say, okay, I will consider 10% probability of exceedance. That means whatever value I consider in my design, there is a 10% chance that that's going to be exceeded. If we make that statement, it essentially means we should look at events that have a return period of around 475 years, and so on. So what you see here, these numbers essentially mean that. And these are generally very accepted norms used worldwide. So we are not, doing anything new. It is something very standard process in doing earthquake-based design. So that is how these numbers come in. Now the only question that is left is, so therefore corresponding to each of these return periods, what are those Z values that we finally get based on our seismicity, the seismicity in different parts of India that we have. So that is the whole process. And that process begins with the whole seismic setup of the country. So essentially, if you look at it, we have a huge the sediment belt, we have the convergent belt, plate boundary, and we have the river deltas, and we have the Indian shield region, and then we have a Eurasian plate. So essentially the Indian plate is colliding with the Eurasian plate. So the first step, as I said,
the entire country is discretized into small regions. About 60,000 grid points were used to discretize the entire country. About 68,000 total events were considered. These are past earthquakes. There were about 26 events which had magnitude greater than 8. And you can see the epicenters marked on this. For each of these now, when we talk about the entire country being discretized into this, there are 3 broad regions, seismic regions which were considered. As you can see, the stable continental region, the active region, and the northeast region. And then there are enough literature and research available that basically demarcates the seismicity of each of these regions to be slightly different from each other. So for each of these, there are certain ground motion prediction equations that were developed, and for that different kind of weightage and logic tree concepts were used. And then once that is done, then finally the entire country was again demarcated into 33 seismic source zones. So, and you can see it also includes the a region in Tibet and so on and so forth. So that we just don't consider the seismicity within the country, but what can come, of course, political earthquakes do not understand political borders. So, that is where it was important to consider that also. And there were some 1831 faults which were considered, including 42 in Sri Lanka. Now, once these seismic zones are demarcated, the basic seismicity of each of these zones were studied. So the recurrence relations for each of these 33 zones were developed, statistical data were generated, and finally the probabilistic hazard assessment process got initiated, right? So in this thing, the uncertainties of earthquakes per se, and then the mathematical uncertainty that is always going to be there in the mathematical modeling, our interpretation of that was also considered. And finally, what we were trying to get were the peak ground acceleration, peak ground velocity, peak ground displacement, contour ratios, contours for the entire country. Now, the interesting part is, worldwide, this whole process of hazard assessment is generally done for 2,475-year return period. Why? Because for 50-year, for structures with 50-year design life, considering 2475-year return period even is equivalent to making a statement that we are going to consider 2% probability of accidents for the maximum earthquake that we are going to consider for purpose of structural safety. So that is the standard practice, and that is precisely what we have also used here. Now, obviously, when you do such statistical study, you will get very, I'll show you the real contours you will have. So then there are processes that are involved in terms of smoothing the data and so on and so forth. So standard processes were done, considering background seismicity also. So these elliptical smoothing and circular smoothing, all these things were done. And finally, we were for every region, the response spectra were developed. Now, these spectra, for instance, you can see the Uttarkashi, Nepal main event, and so on and so forth. So there are already recorded data, and then these spectra were matched, or rather validation was done of the model to see that yes, things are reasonable in that sense. So we got contours like this for peak ground acceleration across the whole country. But then obviously you can see that there are too many contours, too many local bends and so on and so forth, right? Now this analysis, the hazard analysis, is generally done at the bedrock level, and this is something that is significant that has happened in our case. So the spectral acceleration levels were checked at different natural period, right? And then finally, once that was done, then when we looked at those numbers, of course, I mean, we could have stopped at that level. But then there was a need felt to see that we also do a standard deterministic hazard assessment and see that none of the numbers that we have got are way off than general understanding of the seismicity of the region. So that was also carried out. So for each of the source zones, the largest event was considered, taken into consideration, and then again a deterministic seismic hazard assessment was done. The country was again demarcated into different regions. About 60,000 grid points were taken, and then finally we got a deterministic seismic hazard analysis based contour. At this stage, what was decided was finally that this two analysis results that we have got, now we need to put them together and get the final one. So this is what we have as deterministic plus probabilistic. So it is the maximum of deterministic and probabilistic earthquake hazard assessment contour. So what it does is that it gives a higher level of confidence in the final result. And then the most important thing that I mentioned, that all the standard hazard assessment analysis is generally done at the bedrock level. This is where a significant departure was made, and we wanted to get the spectra at the soil level. And so we looked at the entire geological setting of the country also, not just the tectonic setting but the geological setting. And accordingly, you can see these amplification factors. Of course, there were amplification and local pockets were there where there were de-amplification and so on. So again, statistically it was handled. But essentially for different types of geological setting, you can see different levels of amplifications were seen through analysis. And that was considered to finally come up with peak ground acceleration at the surface of the earth. This is a significant step you will not find in many cases, right? So finally, once everything was done, a contour would have looked something like this, which is very hard to use for daily design activity. And so the next process of smoothing it out and finally coming to this zone map, that process got started. And of course there were standard processes, procedures which are there as to how to do the smoothing, how to handle. So essentially some of the key things that I can mention that were taken care of is that no major CT falls on the boundary of a zone, of two zones. If there is an urban setting, it was made sure that the boundary of a zone goes beyond a certain kilometer and they don't fall exactly, and things like that. We looked at the population of each major town and city and took a decision on where to put that. These local modifications were done, but broadly it was a very systematically carried out scientific analysis based thing that happened. So now if we put back all the recorded events and epicenters on top of the zone map, this is the picture. You can see that yes, there are a few smaller islands that you will see, but those are inevitable, you can see. And the most important thing, picture, I think for all of us to remember is the superposition of the zone map with the fault, the active fault map. And if you look at this, you will have lot more confidence in the zone map. So the zone map was done. Now the final thing is, now when you also had looked at the zone map, you also looked at the instrumentation that we have in the country, because the whole process relied heavily on past data, right? And of course, we did not have full record of all motions, because this is very recent earthquakes only we have data. For the earlier ones, we had to rely on other sources. But the interesting thing that you would be interested in knowing is that today in India, if we look at, we have one instrument per 21,000 square kilometer, on an average. Of course, there are regions in the northern, thing where we have a little more density. But if you look at countries like US, Japan, or even Taiwan, of course, it's a smaller island nation. There, they have one instrument per 72 square kilometer. Look at the difference in instrumentation that we have. And this is significant because if we have good quality data, obviously we will have a lot more confidence in our hazard assessment results. But nonetheless, a tremendous job was done over the last 10 years or more than 10 years to finally come up with this particular zone map. And so essentially, now if you see here, earlier we used to have 4 zones, 2, 3, 4, 5. Now we have 2, 3, 4, 5, 6. If you are wondering what happened to zone 1, the idea was that, of course, when we began, we also had a zone 0, right? We had a zone 0 and we had zone 1. It gives a feeling that these regions are non-seismic. But if you remember the fault map, we have active faults almost everywhere in the country. So it was not to give or convey that sense of, thing that, okay, this part of the country is non-seismic. No, there's nothing. So that is why we continued with, starting with zone 2. But essentially, if you see, the entire thrust boundary is zone 6 now. The dark chocolate color that you see, starting from Kashmir, Jammu and Kashmir to the northeast, and most importantly, Andaman and Nicobar. We are going to have a lot of strategic facilities coming up there, and it's a very, very important place to take care. Right? So, what are the implications of this whole work that has happened over the last decade or so? So as I said, what you are seeing is the output of a kind of a hybrid method where this deterministic and probabilistic hazard analysis together has been used in tandem, and then finally we have this zone map and thing. Now, for practicing engineers, the important part is, okay, zone map is the first part. The second part is, what is the zone factor? Then the zone factor values, if you see, now these are the values of acceleration, the horizontal ground acceleration in each of these zones that you see. Now obviously a quick comparison of these numbers with what we today use will obviously give a surprise. And what happened? I mean, how come 0.36 become 0.75, right? But then, as I said, we need to understand how we are going to use this. The interpretation is important, and these values are those corresponding to 475-year return period events. And how does that come into the design aspect is what we are going to also discuss in the next part of it. But before that, some important GK kind of thing. If we see today, if you look at this table on the right hand side, right, we have in seismic zone 2, we are having around 28-30%, I will say 30% of the country is still in seismic zone 2. But then seismic zone 3 has earlier been about 33%, and even today is 34%. And this is where many of the major cities and towns are, right? So that is something that we need to take care. But then what we have is the remaining 1/3 is basically seismic zone 4, 5, 6. And this is where the actual action is. So if you think of it this way, that it's 1/3, 1/3, 1/3 primarily in terms of land area, right? Where we have regions of real high seismicity, and then the middle 1/3 is where all the important towns and cities are, all the major infrastructure development is, with reasonable seismicity. And then we have seismic zone 2, where yes, the seismicity level is relatively lower, but we cannot still declare it, insignificant. So that is the big, macro thing that we can all take back today from this whole thing. But the other important aspect is, systematically done for different types of soil with different, VS values, and all that was done. The other important aspect, talking of infrastructure, is that a lot of our infrastructure, while all this is in terms of horizontal ground acceleration, a lot of these infrastructure like piping and all also needs vertical ground acceleration. That is also important. Until now, we have been using a fraction of the horizontal ground acceleration in our design. So since right from scratch, a very rigorous analysis was carried out, so it was time to systematically look at and develop vertical ground acceleration spectra also. And so you will see that this particular spectra, this variation is given. It's not a constant fraction, but there is a variation that you will find coming up there also. So again, this is a new or addition that we will find in 1893 part 1. Again, statistically, these were all tested for each of those 33 seismic zones. They were developed, and so on and so forth. All the standard processes were followed. And so finally, this is the horizontal ground acceleration spectrum that you will find. And you will see that there is a small portion which is here up to 0.01. Then there is a linearly ascending portion with up to an amplification of 2.5. Sorry. And then, of course, we have the plateau part, and then there is one drop up to 6 seconds, and the spectrum is going to be given up to 10 seconds. Now, 10 seconds obviously is not for regular structures, buildings, and so on and so forth, but there are flexible structures like pipelines and so on and so forth, which can have longer natural period. So, the scope is now, the spectrum will be given up to 10 seconds. And also the issue of damping is going to come back. So there are possible, for different values of damping, it can be modified. Now let us come to these values that we saw of Z. This 0.15, 0.3, 0.45, 0.6, 0.75. These are the values to remember. But as I have been saying, these are values corresponding to 2475. So what happens if we consider, let's understand this, for I see a lot of younger people, and probably, I don't know, students are also probably here, so just for their thing. So event which has a higher return period is a bigger event. An event which has a smaller return period, that means it occurs more frequently, is a smaller event, right? Very infrequent event means it's a very rare, very big event. So there is a trend, there is a natural trend that if a bigger event is this, a smaller event size, how does that variation work? So when you look at events of smaller return period like 975 year, 475 year, and so on and so forth, if we have got the value for 2475 year return period, it is possible to step back and get these values and also go beyond. So that is how the Z values, the same Z values, zone factors for different return periods can be obtained. Now, this again was tested, and this follows what we have and what was ensured is that this follows the global trend also, right? Of course, you can see that the numbers are rounded. You will never get, when you do such rigorous analysis, you will never get exactly rounded off 0.15, 0.3 and perfect. So though these numbers are rounded, but the trend is, perfectly in place, in order. And so we get these lower values of Z. Now, the important point to remember is that all structures we distinguish between the relative importance of failure of a structure. So for instance, if it is a very critical infrastructure, let's say your main bridge versus a regular building. If that building gets damaged versus if that bridge gets damaged, the implications are going to be very, very different, right? So therefore, you can think of it this way, that you would be okay to take little higher risk while designing that simple building, but you would definitely not like to take higher risk when you are designing that critical infrastructure. So therefore, the statement that is made is that regular normal structures can be designed for 475-year return period events. Important structures can be designed for 975-year return period events. And only the lifeline critical structures can be designed for 2475 years. There are another category of special structures which can be designed for even higher return period events. Right? So that is the whole idea. Now, what is normal, what is important, what is lifeline? Remember that table of different parts. So for buildings, the particular group will define which type of building they will call as normal, which type of buildings they will call as important, and so on. Similarly, the bridge will define their normal, important and critical lifeline bridges. Water tanks, they will define which size, which type of water tanks will be called normal water tank, which type will be called important water tank, which group will be called lifeline, critical and lifeline water tank, and so on and so forth. So that is the general strategy that is going to be adopted. So how do we do the design? We have got the zone map, we have got the appropriate Z value we need to pick depending on the structure, the type of structure. And then obviously we have to go to the design spectrum. Based on the natural period of the structure, we get the acceleration. Right now, today we call it SA by G value. So that acceleration coefficient we are going to get similarly, and that will give us the horizontal acceleration, design acceleration coefficient. And these values, these things will come in parts 2 to 11, where part 2 is going to be on buildings, 3 on liquid retaining structures, 4 on bridges. Retaining wall is probably going to go away into a separate part. 5 is going to be industrial structure. So you can see there is going to be a renumbering also, right? Because building is now has been brought into a separate part, which we are going to discuss next. And then we have case isolated structures, buildings, pipelines, dams and embankments, coastal structures, steel towers, tunnels, and we can keep on adding more and more type of structures as we move forward as the need arises. So that is the whole strategy. So that is where we get the elastic force. And now from there, we know in seismic design, we also use R factor to reduce the elastic force to a design force level. So again, the R factor now will be coming from the respective parts depending on the type of structure and the type of structural system that will be permitted, along with the design and detailing specifications for that particular type of structural system for that type of structure from the 13920 vertical. Right? So 13920 vertical will give the specifications for design and detail. The corresponding value, for those systems, the R factors will be provided in the corresponding part of 1893. So that is how we get this. That is your strength design. Now, of course, we also talk about serviceability. Here again, what happens is serviceability is basically for a lower level of shaking. It's not for that same level of earthquake shaking for which this strength is going to be designed for. So we have that. So that is where you will see EED means strength design and EES means serviceability level earthquake, which is going to be a lower level of earthquake shaking. That's the first part. The second important thing that you must note here that in the load combinations, we do not have anymore a load factor of 1.5 or 1.2 and so on and so forth associated with the earthquake load. Why? Because, and we are going to discuss that in detail, next. But essentially, you can say that today, after doing this hazard analysis, we have confidence on our hazard estimate. We have confidence, much more confidence on our Z values that we are considering, and therefore there is little need for an additional factor to come in and say that okay, this load factor is to partial load factor is to take care of uncertainty in that. All the uncertainties, everything has already been taken care of. So we are not going to have an additional 1.5 load factor, 1.2 load factor and so on. So that's another important thing to know. The next important part, very important concept we need to remember is that we are going to talk about soil flexibility in a more conscious way henceforth, right? In buildings, we have not been talking about, we have these empirical expressions given to estimate natural period, but if you remember bridge code, it says apply, model everything, apply a load and find out what is the displacement. So essentially, particularly in those situations, the flexibility of soil does significantly alter the natural period of a structure. And here the emphasis is to bring in flexibility. Now this is not to be confused or interpreted as the code requires soil structure interaction study to be carried out. No, it is not that. So as a first step, the only thing that we intend to account for is the flexibility part, not the inertia part of the soil, not the inertia of interaction between soil and structure. It is only the flexibility part that needs to come in. So, and then for, because we have a static equivalent linear static method and dynamic method, there is a whole geotechnical group which is looking at all these things in little more detail. Numbers will be finalized, but essentially the idea is to consider soil flexibility and then have appropriate factor of safety for design of foundations and foundation systems. In future, where are we heading? And we'll understand this when we finally close the loop with discussion on IS 456. Today we, as designers, we start with our design stress strain curve of concrete, steel, whatever we have. We come up with a cross section, we do the design, sizing, steel, we do the detailing, and we create members. We finish the detailing, and that is it. After this, we stop, right? Once the detailing is done, drawing is prepared, it is sent, it is constructed, but what is going to be the actual behavior of that particular element, what is going to be the behavior of that structure is something we believe that by following all the specifications in the standards, my structure will do good. Right? It is the responsibility of the codes and the standards to give us a process that will ensure that everything is good, will be okay. So we really do not check actually what is the behavior of the structure. Now, remember I spoke about the third vertical of assessment. Assessment is essentially where we actually need to understand this, right? Where is the deficiency, what is the behavior, if the behavior acceptable, adequate or not, and so eventually in the long run, I'm not saying today, tomorrow, but in the long run, we need to have a process which is going to be a closed loop. And just like any other design, even a design is iterative in process, this process also has to be iterative. I mean, there is no doubt about it. There is nothing to fear about, right? But then, as a structural engineer, what it will lead to is that we will know exactly what's going to be the behavior. And this is where, I know many of you are talking about performance-based design and things like that in future, right? I mean, if the moment you talk about performance, you have to know what is that performance. And if that performance is not adequate, then obviously we'll go back and redo, tweak something, change something so that you get the desired performance. So that process is something that we aspire to bring in future. I'm not saying it's going to happen overnight. So earthquake resistant design, from that perspective has evolved from the earlier basically stiffness based design, very large systems, to strength based design where even 20 years back it was purely force based. So code gave a force, we did the same analysis and finished it off, probably a little bit of a detailing, right? We thought detailing alone is going to make earthquake resistant structures. Then capacity based design is something that was brought in a big way in the 2016 versions. It was already there in the for instance, IS 13920, 1993 already had capacity design, but we never called it that way. We said detailing alone is going to give us earthquake resistant structures because the title was actually detailing, earthquake detailing. But if you see 2016 version, the title of that standard changed from design and detail. So that is the capacity design portion, and you are going to see that in a big way. In future, when you talk about load deformation, until now we are sticking to load, but when you talk about load deformation, we are going to talk about deformation-based design, and finally, a robust earthquake-resistant design in terms of energy base. So that will happen in the future, and that is where we should be able to see and predict the entire load deformation characteristics of a structure, wherein we will be able to, we should first ensure good configuration, stiffness, strength, and ductility capacity, of course along with desired mechanisms and collapse mechanism and energy dissipation capacity. That's the overall big picture that we are aspiring to have. And as a first step, of course, we need to start with the right estimate of hazard, and that is what we are doing. But that's not enough. There will be surprises and situations like this, and that is where it's not just structural design, but geotechnical aspects also become an important role in earthquake-resistant design. Today, when we talk about performance and other things, of course, safety not just of the structure, but also of the architectural elements and utilities of a structure have become very important, because our buildings, our structures are becoming more costlier, because not just because of the structural elements cost, but because of all these elements in the structure. So it becomes an important aspect. So this first part I'm going to close here by saying that there is one major change that is happening in IS 1893 part 1. Well, you can say part 1, the first change is that building is now out of part 1. We're getting into part 2. So that's one change. But other than that, one significant change is the hazard part of it. And that is the one significant change that we all need to know. And then obviously there are improvements in terms of the spectrum, we have a vertical spectrum and so on and so forth, right? So I'll stop here on this. By thanking all of you. I can see this hall full. I'm so grateful to all of you, and particularly to ISSE, SEFI, and this great institute. So with this, what I'll do is I'll move to the next part, which is the building part, and that is where we will see exactly what are the implications of this change in hazard and how do we use that. Okay. So yeah, that's it. Thank you. So we'll just take a 5-minute break. If you have to just go out, come back. At the end of this one, before we go for lunch, if you have any specific question on both these two parts, obviously we'll be able to, I think we should be able to take some questions also. Okay? So, yeah, we looked at the 7th revision of 1893, part 1. And as I mentioned that it had two essentially components. One is the general provisions, which is the basic hazard part, which is common for all structures, and that is what we just discussed. And then we had another component called buildings, which is now going to be in the second part, which is going to we are going to look at now. So this is the change in terms of the seismic zone map. We had 4 zones, now we are going to have 5 zones, zone 2 to zone 6, and these are the zone factors or Z values of 0.15, 0.3, 0.45, 0.6 and 0.75. So increment of 0.15 G. But then the important point to remember is this is for 2475 year written period. That's the important part. Yeah, so these are the two parts we are discussing. And then, as I said, right now we are going to discuss 1893 part 2, which is on the building part. So 1893 vertical, just to recall once more, gives us the demand for design of new structures as well as assessment of existing structures. 13920 vertical is going to give us specifications for design and detailing of new structures. And 13935 vertical is going to give us process of assessment and the decision making pointers whether the structure needs repair or retrofitting. So that is the whole process that is going to come in 13935. So right now we are on part 2 of 1893. Now each of these parts, again for instance part 2, when we talk about part 2, either 1893, 13920 or 13935 doesn't matter. Part 2 is for buildings. But then within part 2 we are going to have sections. So the first section is general provisions for all buildings, because we are talking about part 2. And section 2, masonry, then we have concrete, then we have steel, we are going to have adobe, timber, steel, concrete, composite. At least these are the items that are there in pipeline. Similarly, let's say we are going to talk about water tank. So we can have concrete water tank, we can have steel water tank, and so on and so forth. If you are talking about bridges, you can have masonry bridges, steel bridges, concrete bridges, and so on. Composite bridges, and so on. So that's going to be the uniform structure of these 3 standards. Let's come and look at, so what are the key changes after the revision? Obviously the most important part is that now that we have a new zone map, new zones and zone factors, obviously there is going to be a change in the design, right? Particularly design force, and then load combination I mentioned, but we'll revisit once more. There will be some changes in the serviceability check, and then most important thing that we are going to see, which is already there in, we have the last session on 16700, and those of you, I know many of you actually do a lot of design of tall buildings, so you know that there are certain type of structural systems which are recommended for certain heights and so on and so forth. So similar consideration will come in here in terms of the seismic zone, in terms of only a certain type of structural system will be permitted and others will not be permitted. So that is an important, again, conceptually an important idea that is going to come through. And then we already existing, if you look at 1893, we have provisions on torsional irregularity related items, they are going to be combined together and with an additional item which we are going to look at. So these are the key changes in 1893 requirement with vis-a-vis building systems. In addition, there are provisions on buildings on slope, some preliminary provisions given, because we are seeing a lot of development happening in the hilly regions, and it's for good, for strategic reasons they have to happen. AUs becoming important, and then attention to critical lifeline and special buildings. Now, while all these things are may look like that these are additional requirements involving more rigorous analysis and design, it is also important to ensure that smaller structures need not go through this whole rigor while certain basic safety is guaranteed. So that is where some, I've written the word relief, but essentially a simpler guidelines for smaller regular structures is also going to be part of it, so that we don't worry too much about these structures. So let's focus on the strength design part. So now, and today we calculate VB as per the code, right? Design base shear. So that is basically going to be called EED, earthquake effect, design earthquake effect for strength design. And there we are going to have this Z, which is the zone factor. I is importance factor, but we'll talk about it later in a while. And then AHD is the design horizontal acceleration coefficient, which is obviously a function of the natural period T of the structure. And then W is the seismic weight, and R is the response reduction factor, right? So the same standard format, but the basic load combinations, if we see, now there is no 1.5, 1.2 and all that, because it's directly coming through that. In addition, there is a special load combination where we have this omega times EED. Now, remember, EED, what is EED? EED is the design force, right? The interesting thing to note here is that if, let's say, I design, I have to design a beam. Just think, with me. I have to design a beam for, let's say, 100 kilonewton, just a chota beam, okay? And I come up with a cross section, I provide reinforcement, everything, and do the detailing. And then you take the beam and go to the structural engineering laboratory here and actually test it. Will the beam carry more load or less load? Will it fail at a moment less than 100 kilonewton meter or more? More. The question is how much more? How much more? Sorry? Factor of safety. So the point is, when we say a building is to be designed for that EED force, in reality, the building is going to induce a higher force during that design earthquake shear, because each of its members have higher capacity. Okay? So during that actual earthquake shaking, this actual inertia force that is going to be induced in that building is not going to be limited to that quantity EED, but is going to be more than EED. No. Weight is already there in that EED. Seismic weight is already sitting there, okay? And we will see that again through a, we have seen that, but we will see again in terms of the load deformation graph. So now the point is that during actual earthquake shaking, a higher force is going to be induced in the system. At that, and when that happens, you would not want some key elements in that structure to fail. And when I say fail means not just get damaged, but fail. There's a distinction between failure and getting damaged. What would be, let's say, those key elements? Let's say in a moment frame, where you have beams and columns, which would be the key element, which you do not want to fail? Columns. So the column should not fail. Right? When that higher force gets induced during the actual shape. Let's say you have kept the column fine, but between the beam and the column you have a beam-column connection. Right? When that higher force tries to get induced in the system, if the connection fails prematurely, then everything else fails. So there are certain key elements in every structural system that must stay put even when that higher force gets induced in the structure, because earthquake is actually not applying any force on the structure. It is the force that gets induced in the structure during that earthquake shaking, and that is why it's not a load. It's not like something like dead load that we keep and we know, okay, this much load I have put. Right? Earthquake effect is induced, and that is the what we call as the overstrength force that is going to be induced in the structure. So this spatial load combination that you see with that factor omega is essentially to say that, look, the structure is designed for this EED level, but actually if that design earthquake occurs, the force that is going to be induced in the structure is going to be over and above that. How much is that factor omega that you see there? And when that happens, you do not want certain key elements only in the structure to fail, because that would cause collapse of the structure. So this spatial load combination is only for design of those critical members, depending on the structural system. Okay? Is this a new concept? Answer is no. It has already been there in IS 800 section 12 in steel design code since 2007. The only thing is it was given as a fixed factor of anybody, 2.5. Here there is a new Indian standard on 18168, which is on steel buildings. There you will see that we have segregated that into two parts depending on the structural system. So again, the different parts of different structures is going to give that factor. It's not a fixed factor, but the different parts of 1893 is going to recommend use of a certain factor. Typically this number, this omega, varies between 2.5 to about 3.5 and 4. Depending on structural system, depending on which zone the structure is designed for, what type of structure it is, and so on and so forth. Okay, so that is the whole concept of this spatial load combination. Now let's come to this. Let's forget about that spatial load combination. Let's look at the basic load combinations which we all follow. So now my normal building I will design for 475 year return period event. So when I'm designing a normal building, what is normal building? Let us not worry about at this stage. Let's say it's a normal building. And let's say we are in seismic zone 3. So what will be my Z value? 0.15. It's not 0.3. Okay? But if I'm designing an important building, then it will be 0.2. If I'm designing a lifeline building in seismic zone 3, then my Z factor will be 0.3. So you can see that it is almost like this, putting these different categories of buildings into different return period columns is almost like incorporating the importance factor into it. So in essence, by taking this approach, there is practically no need for an importance factor separately anymore. So by default, importance factor for most structures is going to be 1. When I say structures, I am talking about different parts, buildings, water retaining structures, bridges, and so on. So by default, for everything else, everything it's going to be 1, except when within the same category you want to still make a difference. You can add a little higher importance factor to few of the things. Okay, but in otherwise we don't need an explicit importance factor for this. If we put them into these different verticals, depending on the type of structure. So that's the first part. So you will find this table where it says that for strength design, the first column. So building set 1, which is normal, 475, bridge set 1, 475, and so on. Then 975, then 2475. What goes into each of these sets will be defined in the respective parts. Now, if you look at these values, I said there is a global trend, and that global trend is essentially this. So remember, hazard analysis, the standard is to do that for 2475 year return. And then we calculate the corresponding values for the other return period based on this scaling factor. Okay. Now here, if you see, if 2475 year is therefore 1, if I'm considering it to be 1, in seismic zone 2 and 3, which are low to moderate size regions of seismicity, the 475 year return period is actually half of that of 2475. That's why we got 0.15 instead of 0.3, so it's half. But in zones 4, 5, 6, which is regions of high seismicity, it is 2/3. So you can think of it the other way. Say that if 475 is the benchmark, then 975 and 2475 are in that proportion. Whichever way you are comfortable, look at it that way. Importance factor is generally 1. So directly, you pick up the value of Z and you do your calculation. In buildings, for buildings, you see that there is a little thing of 1.15 which is sitting there for residential buildings with certain occupancy and all. The whole idea is that with that importance factor, you should not jump from one return period to the next return period. Then you might as well say that, declare that particular structure to be of the next category. But within that vertical, if you want a little adjustment, that is possible. So that is the thing. So basically Z and I together gets, does the work, and we do not need an explicit I. Now, this R factor, again, there is a change. There is a slight change, I would say. In general, you will see that we have now listed a lot more structural systems, and the corresponding design and detail for each of these structural systems you will get where? In 13920 vertical. 13920 part 2 and corresponding section, depending on whether it's steel, concrete or whatever. But in general, there is a slight increase because we are more confident now of not only hazard but also our design and so on and so forth. We'll see. This is the design spectrum. And now the important question that is there in almost everybody's mind is, so what is the implication in terms of our design? Because I see mostly practicing engineers. So let's look at that and understand that very, very quickly. Currently, this is how we calculate our design force. Essentially, if we just take the basic dead load plus earthquake load combination, so you have a load factor of 1.5, we do Z by 2, we have I, R, and thus SA by G essentially, right? If we look at that, take that, and if we assume that our basic design is for when we do Z by 2, the understanding is that we are talking about a design for what is called a design basis earthquake. There are many texts available which talk about that. And that basically is for 475 year period. Sorry, I'm just, give me a minute. Okay. So now, if we take that, let us look at buildings. Currently, we have these three importance factors for buildings: 1, 1.2, and 1.5. So for normal buildings, when we take importance factor of 1 and multiply with the load factor of 1.5, we get a total factor of 1.5. And if we see 475, if we take that as the benchmark, we essentially mean, what it essentially means is that we scale that fact value and go to a hazard level corresponding to 2475 year rating. This is our current practice. But when we use an importance factor of 1.5, 1.5 times 1.5 is 2.25. Essentially, the hazard level, if we start from 475, it actually goes to all the way to 10,000 year return period. I mean, as practicing engineers, do you think that this is what we are doing today? We are doing it, but we are not aware of it. That's the difference. More interesting thing happens if you look at water tanks. So today we have these factors, right? And it says greater than, importance factor greater than what is given can be adopted. So then you are basically going even more than that. Bridges, we have all these. So if you think Z by 2 is DBE 475 year, then essentially by doing that scaling, we are going all over the place. 2475 year return period, 5000 year return period, 10,000 year return period. It makes no sense. Industrial structures, importance factor 2. 2 times 1.3, 1.5 is 3. Right? The question is, are we really designing for such high level of hazard? Answer is theoretically yes. Yes, thank you so much. Little bit up. The answer is theoretically, if you think that Z by 2 corresponds to 475 year return period, by having a load factor of 1.5 and an importance factor of 2, you are actually going beyond 10,000. But the only savior was that our Z value today was grossly underestimated, and so far, even after doing all this, the value that we were designing for were reasonable. This is actually a proof that we have been using a grossly undervalued value of Z until now. And that is why we needed all these importance factors of 2 and load factor of 1.5 to get reasonable value of design force. So, and most of it was happening because we are just following it. We went, yes.
So what is the basis for this differentiation in buildings?
Which,
normal, important, like.
yeah. So we can. So that is what I said, that each of these parts will define which class of buildings to put as normal. Let's take a simple example. I mean, you were talking about regular government housing, let's say 4-story, 5-story buildings, versus you are designing, let's say, a telecommunication building. Right? Both are buildings. This is a residential, that is a telecommunication, and that too in a, let's say, a hilly area where that important functionality of that building is so important, because otherwise everything will get cut off, right? So you can say that this is a critical and lifeline structure, whereas the other structure, another is an important structure, and so on and so forth. So there are ways to categorize each type of structure into these different types. So this is what, similarly stack-like structures, and then so in summary, right now we are using a total factor, a multiplying factor anywhere between 1.5 to 3. Instead of that, the proposal is that anyway importance factor is going to go away. It's already going to be taken care by placing different types of structures of different importance, if you wish, under, and designing them for different levels of hazard. And that will be a conscious decision by the engineer. So you as an engineer will know what exactly you are doing, rather than just relying on some multiplying factors and not knowing what it means eventually, right? So that's the whole idea. Essentially, in any design, we place importance to different categories. So when you say normal structures, important structures, critical, or buildings, important buildings, can be hospital, for example. A hospital building, you can define that this is an important building and not just a regular normal building, right? And give it more importance, so to speak, and therefore ensure that it is designed for a higher level of force, and you basically guarantee little more safety in that sense. The moment you design a structure for a higher level of force, essentially means for that smaller level of earthquake, that structure is not going to get damaged and remain functional. So functionality comes into the picture, right? And that is why we need to do this segregation. I hope this part is clear. So, in general, that is where the whole structure is: normal, important, critical, and lifeline. And then there are certain types of structures which can be classified even as special, but that scope is already there. So with this kind of structure framework, it is possible to now incorporate or follow the same standard procedure for all various types of structures consistently, right? Without any introduction of ad hoc multiplying factors. That is the whole idea. Now, why 475? What are these magic numbers? 475, 975, and so on and so forth. Essentially, because there are three parameters involved. One is what is called the design life. The other is what is called how much exceedance you can afford to allow in your design. And third is what is the return period of a natural event. Return period can be just like when you talk about 875 part 3 wind code, right? It says the wind considered is of return period of 50 years. It says clearly, right? So similarly for earthquake, we consider these numbers. Why? Because then for 50-year design life structures, 475 essentially gives us a round number of 10% probability of accident. That means the Z values that we have considered, there is 10% probability that those values of Z would be exceeded during the design life of the structure. It doesn't mean they are going to happen all the time, but that is the 10% probability. 975 means 5% probability of accidents. 2475 means 2% probability of accidents. Now, the same thing today, if you say, no, but my hospital building, I want to say that it is of 75-year design life. Or my bridge, for instance, is 100-year design life. Then what happens? Okay, 100-year design life, but you still want to take 10% probability of accidents only in your design. Then you have to go and design for 975-year return period. So you can see that a 50-year design life building designed for 475 year event, and a 100-year bridge, design life bridge, designed for 975-year return period event, essentially means in both the cases you are taking 10% chance. Right? So with this table in front, we know exactly where we are pitching our design. And that is the most important, conceptual thing that is coming up in this revision. And I'm confident that once we understand this, we will be more informed design engineers than we were earlier. Now let's come to numbers, very important part, because this is what matters for our daily activity. Where do we stand after all this revision, all these conceptual things are good, but finally bending moment, shear force ka kya hoga? So let's look at that. So let's take example of a normal building, decrease in Z value. There are, it's a mixed bag. But in terms of final design force, and when I say design force, I'm not comparing VD, I'm talking about 1.5 times VD, because that load proposed revision, what is going to happen? Zone 2, it's going to remain same. Zone 3, there's going to be 25% increase, and so on and so forth. So around 50% increase in design force is going to happen. Right? But then there is a little catch here. Remember, our zone map itself has changed. So when the zone map changes, and earlier we had 4 zones, now we are going to have 5 zones. There are towns and cities where earlier they were in one zone, but in the revised zone map, they fall in one zone higher. So if that happens, there is going to be this amount of increase in design force. And in fact, there are 12 such towns with population, if I remember, greater than 2 lakhs or some number, where they actually go into 2 higher zones. So in that case, this is going to be the change in design force. So this is the implication finally. Yes, it's going to happen. If you talk about important buildings with importance factor of 1.2, if we just have to map them, suppose we try to map them, that importance factor of 1.2 is now 975-year important, right? Then if they are in the same zone, again you see on an average it is around 50% increase in design force. If it unfortunately goes into one higher zone, then yes, around 100 to 120%, 150%, and if it goes into 2 higher zones, then there will be this increase. And critical and lifeline structures, again something like 50%. So most of the structures which stay in the same zone, you are going to see something like manageable 50% kind of increase in design force. That's going to happen. If they fall and jump off into higher zones, then of course there is a double impact. One is there is a slight increase because of the Z factor itself after all the adjustments, and then there is a impact of getting into higher zone. Is this going to happen for the first time in our country? Answer is no. If you look at all these 5 zone maps, some town, some city or other has always gone through this. They were earlier in one zone, and then after the revision of the zone map, they went into another higher zone. It has happened in the past also, it's going to happen in the future also. There will always be a transition period, but eventually things will settle down. Right? Today we don't worry about that, what happened in 62 to 66, 66 to 84. Today we don't worry. So similarly, we'll settle down with this also. So that is about strength design. Serviceability. Now, coming back to this overall load deformation graph, if you see, that is the overall lateral force, lateral deformation graph, assuming, as a cartoon there. When we design, this is precisely what we are talking about. So, your design EED is basically here, and this is the design strength. This is the design strength of the structure. Serviceability is obviously one, a level lower. So we are talking about smaller level of shaking and smaller level of forces. So that is going to be there. But look here, the actual strength is higher. This is what we are discussing, that if I design a beam for 100 kilonewton meter moment, that beam is always going to carry more load than 100 kilonewton meter moment. And so is the structure, because the structure is nothing but collection of so many beams and columns and walls and everything else. So if this is the design strength, this is the actual strength. And that is that factor, that omega factor that you saw is basically that jump. Now, of course, one important thing that is coming up is that, and then the horizontal part is basically the ductility that we aspire to provide by following specifications for design and detail given in IS 13920. Right? Now, what happens is that this portion of serviceability check is essentially to ensure that our structure has certain stiffness. Stiffness is important. We saw after configuration, then we have stiffness, then strength, then ductility. So stiffness is important, and that is where this comes into the picture. What is given currently? Currently we have one number for all zones, right? For building systems, interstory drift under the design force, unfactored force, 0.4% interstory drift. The proposal was to have a graded approach so that in the higher zones, particularly zone 4, 5, 6, we provide more stiffness, because the displacement demand is going to be significantly large. We are looking at the acceleration part only. Correspondingly, if you look at the displacement spectra, which is going to come in future, then the displacement demand is also going to be larger, and that warrants a higher stiffness. And so the proposal is to give a graded requirement of stiffness. But anyway, this is under discussion, and numbers, of course, let us not worry about the numbers at this point in time, but conceptually this is how it has come. Okay, instead of a single value, a graded stiffness requirement. So that is where the whole thing is. In terms of analysis, modeling and analysis, IS 16700 actually paved, is the leader in that, because it actually gave that, okay, strength and serviceability, two different models with different section modifiers. Similar strategy is going to come in, and we are all comfortable with it today, so no issue with that. Structural systems, very important change, or conceptually, this is very empowering in the sense that today, for instance, in masonry building, we have 4 basic types of structure, masonry buildings. What are those? Masonry walls with bands. Masonry walls with bands and horizontal and vertical reinforcement. Confined masonry and reinforced masonry. So what you should note here is not all these details, but unreinforced masonry is prohibited. That's the important point to note. No more unreinforced masonry in the country. That's the part. And then, depending on the importance of the structure, if you say normal, important and all, and different zones, you have a matrix of which type of masonry is permitted, right? So as you come to the higher zone and as you move towards the right, more important structures, you see that finally in the right hand side box, you are left with only reinforced masonry. Because that only will survive under severe earthquake shaking, right? So this also is an important way of understanding the strengths and weaknesses of each structural system, each type of members. For reinforced concrete, for instance, again we have 5 types. What are these 5? ordinary moment frame. What is ordinary moment frame? A moment frame designed as per provisions of IS 456 alone. Then we have special moment frame, one that is designed and detailed as per provisions of IS 13920. Then special moment frame with special structural wall, designed and detailed again as per requirements of IS 13920. And then dual system, where you also ensure a certain proportion of strength between the frame and the wall in addition to the design and detail portion. So again here, if you see normal buildings in seismic zone 2, all structural systems are permitted. And now to this we can also, you can think of adding one more layer of 16700 tall building coming into the picture, right? So that is another layer of complexity you can add. Here, of course, we are talking about regular, buildings. We are not getting into the ambit of purview of tall building code. This is regular, normal structures. And by the time we move to seismic zone 5, 6, and particularly critical lifeline structure, essentially dual system means that we need to have structural walls also, and not just any structural wall. And what is structural wall, we are going to see after lunch when we discuss 4, 5, 6. Essentially for now, I'll stop by saying that design and detail as per requirements of IS 13920. Right? So in 2016 revision, significant improvements were made in these provisions. They will continue with minor modifications. So when you talk about requiring structural walls, there is a requirement of how much wall in each principal plan direction. Currently, we have one fixed number of 2% for all zones, all type of building in IS 1893 2016. Probably again there is a feel that it is better to have a graded approach to that than one fixed number for everything. So anyway, these numbers are being looked at also. Similarly, steel, I mentioned that parallel to 13920, there is a steel code which is published, IS 18168. I don't know how many of you have seen that. Essentially there again you will see that 3 essential types of frames that are given. One is the moment frame, ordinary and special, concentrically braced frame, ordinary and special, and eccentrically braced frame. So ordinary moment frame and ordinary concentrically braced frame are those which are designed and detailed as per provisions of IS 800 alone. Not IS 800 section 12, but except section 12, all other provisions of IS 800 alone. Special moment frame and concentrically braced frame are those designed and detailed as per current provision of IS 18168. And eccentrically braced frame, of course, is only given there. And there you have this graded approach of allowing structural systems. In terms of irregularities, we have 12 irregularities currently in IS 1893 Part 1 2016. The entire thing is rearranged a bit, and now we are talking about torsional flexibility also, an additional component I'll touch upon briefly, and then more or less the similar things. No significant change except one aspect, which is this flexibility factor. Little detailed it appears, but essentially let me try to give the essence of it through this. So what I always look for is the stiffness distribution, eccentricity between center of mass and center of stiffness. So that part we all look at, and that is our eccentricity. And we also have a provision of design eccentricity to be considered in design. So that is one aspect, that is when a force acts as a static force, that eccentricity causes a torsion about the vertical axis of the building, and that action needs to be considered in terms of additional shear force and bending moment on columns and so on and so forth. So that part is already there. But what happens in addition to that is, during this back and forth oscillation during seismic shaking, there is also an amplified action due to distribution of non-uniform distribution of mass. So that is the rotational flexibility component that comes into the picture now. So it's a dynamic component which is there. And then of course we have the separation between different modes of oscillation between translation and rotation. So T theta Tx, Tx is translational mode of vibrations natural period, and theta is the rotational mode, the torsional mode natural period. That separation is also important, which is all again existing today, right? So that's why I said that on at least 3 occasions the issue of torsion is handled today in various clauses in 1893. Now we have this rotational flexibility component brought in, and then the entire set is tried to be brought into one simple thing, which is this. So essentially with this parameter psi, what happens is that you get to know whether the building needs additional 3-dimensional torsional analysis or not. If you have a regular structure to begin with, then of course everything fine, it goes okay, right? Otherwise, depending on your total torsional eccentricity and the natural period ratio tau, which is P theta by Tx, you get to a matrix where you see what is required. Beyond a certain limit, of course, we will continue to say reconfigure, redesign the structure, right? Some chota mota is okay, but you can't commit a murder and then get away. So that's the whole idea. But essentially, this is the whole concept. That is, may appear slightly differently in the proposed revision, but essentially the concepts we all understand. So 3 factors which are interlinked: torsional eccentricity, rotational flexibility, and torsional flexibility. All 3 put together in that compact form is what you will see, and we need to talk about. Okay. Coming to the last few items, building on slope. This is something new that is proposed. Essentially, what happens is that when these buildings, we talk about, currently we have 12 eccentricities, irregularities specified in 1893 part 1. If you look at these buildings which are on slope with non-uniform level of foundation, you will find out of 12, 8 eccentricities definitely exist, all in one building. Okay? Out of those 12. The only way to save, therefore, these buildings is to provide structural wall. This is like that old, shampoo had 5 problem, 1 solution. This is 6 problem, 1 solution. Provide structural wall. Okay. So the idea is that, and the most important aspect is torsional irregularity. Okay, in this, because one side is stiffer, the other side is flexible, so torsional irregularity, and that is where the whole game of providing structural wall comes in, and that is what is the recommendation. So basically, you can do a basic static, you calculate the design forces, apply the forces, and if you see that in your analysis model, 3-dimensional model, that the ratio of the 2 displacements at the end exceeds a certain limit, then you add structural walls such that that ratio of displacement comes down. And you know that you have provided optimum amount of wall. That is the whole idea. These architectural units, elements and utilities. Obviously, there are basically designs to be done. Some are acceleration sensitive, so basically heavy objects have to be anchored, otherwise they will slide, topple, and things like that will happen, causing damage. So there is a design force to be calculated, and they have to be designed for that. There are displacement sensitive things. For instance, you're in a hospital between 2 expansion or seismic joints, you have a gas oxygen pipe going through. So you do not want that pipe to break when the 2 components of the buildings oscillate back and forth. So there are displacement sensitive designs to be done. in things like that. And then there are components which are both ways. You have one massive portion on settled, fixed on one side of the building, and then there's a pipeline, long pipeline going to the other part, and so basically requirements for design of both acceleration sensitive and displacement sensitive things are given there. So you can see examples of displacement based design requirements supported consecutively at 2 floors of the same structure, different structures, adjoining structures, and so on and so forth. Special buildings, critical and lifeline buildings designed for 2475-year return period. Special buildings actually, I'm not sure, we may not even have a category like this, but they are for other structural systems. Remember, part 2 is for building, then part 3 is water tank, and so on and so forth. So we are going to have a lot more different structural systems coming in. So for some of them, we may even have some special structures that need to be designed for even higher, as high as 5,000 year or 10,000 year return period. I mean, 2 quick examples that I can give you. One is, of course, dams is a very special class of structure, and some nuclear facility structures are there. But those are not covered directly by this standard because they have their own respective bodies to define their hazard, but there are possibilities for those. The other important aspect is liquefaction potential assessment. 2016 brought in, there were some issues, some modification, revisions are going to happen, but that is one important aspect which is going to continue to be there in 1893. Unstable hill slopes, that is something that we need to also worry about, because if the hill slope falls, obviously even providing walls and everything for that building is not going to help, because the whole slope will sweep away the whole thing. These are other, tsunami or flood prone areas, adjoining unsafe buildings and structures, accessibility. These are issues that are under considerations, that there may be provisions directly or indirectly. We'll see how it goes. But essentially, in terms of structural systems, we have other issues like base isolation. So we have a standard for base isolated buildings, right? And that is also something that will eventually come into part 2 because it has to refer to that standard, right? So part 2 is because it is on buildings, it has to refer to that. And then the most important thing is that there are certain structural systems which we'll talk about in IS 456. But as far as this is concerned, the main lateral load resisting system component of a building should not have flat slabs, pre-stressed floors, precast method of construction. These are still not, there is not enough confidence, so to speak, to allow these things. And so these are going to be out of the purview of 1893 for some more time, if I may put it, in that manner. Of course, unreinforced masonry we have talked about. So these are the important aspects that we, in terms of structural systems, we have to see. A lot of emphasis is going, it has already happened in 2016 revision, that 3-dimensional analysis, because we are building more and more complex structures, buildings. So to capture such complex behavior through simple 2-dimensional analysis is not adequate anymore. So that is where we will have to rely on some of these things. I know that there will be a need for some of the very popular structural analysis softwares also to update and provide solutions based on the new requirements, and I'm sure that will happen in due time. As I said, some small buildings are buildings up to 2 stories, so that infill walls, there are certain requirements of saying that okay, at least 90% of the base should have infill walls. Equivalent static analysis is required. No need to do all this analysis. What is the definition? Will it be 2 stories or 3 stories? Is still under consideration. Don't worry about that. So in summary, in closing, I'll say that structural system is now in focus, right? And this is where I, coming from an academia, I see that all the time we teach analysis and everything, design of only moment frames. I think we have to change first, right? And standing in an academia, in an engineering college of such repute, I think this is something that we have to consciously start doing, because we need to prepare the next generation of engineers also, so that they are able to use it. We can't just teach moment frame and then expect them to design all other systems. So that is something that we look at very seriously, and I think it's important for structural engineers to understand. The design method is basically the same, but calculations are little here and there. The importance factor is no longer so important, because you are directly going to take the Z value appropriately depending on that, and then we are going to have these new provisions on this, right? So this is in brief, without getting into the details of everything that is there, the broad changes that are coming up, that are proposed in the part 2 of IS 1893. I'll stop here. And we are just at the time, we have 5-10 minutes for question and answers. So I'll stop here for now. Thank you. If there are some questions, I will try and answer.
So, have anybody prepared some sheets about the questions? You can pass on your sheet. Okay, Mr. Rao, please speak.
Design is based upon assumptions and hypotheses. So, is there any structure, in India or because it's still a high intensity earthquake, a really important structure where it is falling in the earthquake zone, and after all incorporating all these solutions, must have withstood the high intensity earthquake, and it's still standing in spite of the earthquake.
Of course, there are many. There are thousands and thousands of. No, I mean, let's take example of recently also in Japan we had a major earthquake, right? And the structures are standing. I mean, of course, it's a very rare thing for Japan to have fatalities, 70 plus, which is very unfortunate. But at least you don't have collapse as such of major. Yeah, see, this crane is standing. I said this is not science, this is miracle. So structure standing is miracle sometimes. But coming back to your main intent of your question, I mean, definitely there are enough number of structures in the west coast of US, Japan, New Zealand, right? Which are designed and they perform excellent, very well, and I think that is what we should do.
These structures on the slope is more focusing here.
No, it's just it is there, because we think that there is a lot of development happening in these hilly areas because of our strategic defense and other things, and it is time that we pay attention to these structures also and ensure safety of these structures. Explicitly, we thought, Indian standards start talking about it. Otherwise, I know there is a lot to be done in terms of regulation, bylaws, and so on and so forth. But somewhere somebody has to make a beginning. So, Indian standard is making that first step, hoping that there will be other things that will be taken care of. But if we don't do anything here, then we are leaving those structures to be, continue to develop in a very unregulated way, in a very unsafe way. We may be held accountable for not doing enough later on.
for the sloping is again different, but there should be a slope assessment.
You are absolutely right. It is essentially the slope angle and the number of days. So if you look at both of them, generally in these buildings, if we go across the, the boundary, it will be 3 or 4 days maximum, and for different angles. So essentially, both these together boils down to the level difference. So instead of saying who's going to measure the slope angle, right? But as an engineer, you can see, okay, this is the level difference. Yes, you're right. You're right.
One more thing, sir. Importance factor for normal building, there is 1.15 importance factor. And for important structures, it is 40.
Come again? Sorry.
Importance factor in the normal structures, there is 1.15 importance factor mentioned. Whereas for the important structures and critical structures, it is 40.
Yeah, that's what I mentioned. It is normal buildings, let's say, but with the higher occupancy, you want to give it little higher importance. You don't want to call it as important as a hospital building, let's say. So if you jump to the next one, your multiplying factor is 1.2 and 1.25. Here, you want to keep it at that level, but little higher than a lower occupancy house, let's say. So that is why that finer adjustment, for that finer adjustment, I want that value is given. We may choose not to use that also. Perfectly fine. Last question, because I see hands from the other side.
Damping ratio is same for
Okay. For the purpose of design, see, why it happened in 2016, let me say this very clearly. This standard 1893 is for design, is for calculating the design force. Right? If we give different design values, so let's say I have a steel moment frame building with concrete composite deck and some masonry infill walls and glass facade exterior. Which is the material of construction and which is the value of damping, that is appropriate. There is no correct answer to these questions. Right? So, for ensuring a level playing field, for the purpose of calculating that design force alone, it was said, consider 5% damping for everything. So that if you are going to bid for a concrete building and I am going to propose a steel building, I am not at a disadvantage of having to design for 40% more force. I'm never going to get that job, because my starting point is 40% higher force, right? So that is the whole thing. Why damping is coming back in? Because this general provision is going to be not just for buildings but for all those systems, and there are nuclear facilities also which are going to be designed using this. So therefore, for those kind of situations, the damping factor is brought in so that depending on the type of special industrial structures and so on and so forth, the appropriate value of damping can be considered and design can be done. Yeah.
Interstory rate, why is it zone dependent? Because it should be critically applicable to AUs, right? It's not for the structure alone.
Yeah, true. So if we look at the existing one, that is considered to be enough for protection of AUs. And that's why I said the focus now shifts from non-structural to structural. And the focus is now on stiffness, ensuring that structures in higher seismic zones have little higher stiffness.
But it's still work in progress. There is.
Yeah.
I must assure you that this is work in progress. It's not final.
Yes.
So there may be changes. Okay. So just rest.
Generally not considered in a seismic event, but it's generally a strength event.
I agree.
So here, what just as a calibration point of view, at least what we saw is that the stiffness requirements are decreasing as compared to the older codes. Because you are using the stiffness modifiers which are completely almost uncracked, and you are reducing the forces as compared to the current.
No, that shouldn't happen, but thanks for that input. Yeah. I showed you that overall harmonization plan, right? We don't want to bring out only 1893 part 1 and create panic because the corresponding 13920 is not out, not ready. How are you going to design? So at least the building portion or water tank portion, at least few structures we want to make ready the entire set and then bring it out. Otherwise, if you just give these Z factors, then it will become very difficult for you to design if you do not give the corresponding 13920s, for you to work.
How long it will take in case?
We definitely plan to bring this within 2024. This year. Definitely. Let's see. Vertical natural period. I guess I've got some questions. I'll go through them over lunch, and then I'm sure we'll have opportunity to answer these questions later, if that is okay with all of you.
So actually time is running short. You can write your questions on the sheet and hand over to us. Definitely your questions will be answered. So time is running short now. Please be seated at the place. There is one small presentation by Ultratech. So before that, Rupesh sir, he woke up at 3 o'clock in the morning and he came from the Chennai to this Mumbai for imparting the knowledge and explaining you the broad changes, key changes of the science. Really, he has taken a lot of space to come here. So, on behalf of the organizers, I sincerely express my sincere thanks to you, and we expect much more interaction in future also. Thank you very much, sir.
I'm going to come back after lunch.
That is also there.
Thank you.
Thank you very much, sir. And now our technological partner, Mr. Ultratech Cement. So their officials are here and they want to showcase their products and give some presentation about the future of concrete. So I request Engineer Satyaki Sarkar, National Head Technical Services and Joint President of Ultratech Cement. So I request Sarkarji to take charge of the mic and
Hello. So very good afternoon to all of you. I don't want to stand between you and the lunch, so I'll keep the presentation very brief. It's just, to take you through a journey of Ultratech. Like we have come a long way in the last 2 decades, say from 3 million tons to 140 million tons. And all that has happened because of the support and the cooperation that we have received from all of you, all technocrats and architects. I'm very happy to see Jain Saab, who has been a guru for all of us, till the formative days of Ultratech. Jain Saab had been our not only friend, philosopher and guide, but he was an institution himself in civil engineering and building materials. So thank you, sir, for being here. And I will quickly take you, see, Ultratech is growing by every day. Every day has been a story, a new story, which comes for Ultratech. I am with this company, with the Aditya Birla Group for the last 25 years, and I have seen each and every day. Okay. Okay, I don't. Each and every day, there's something happening. Now, if you see that, though we are a cement major, we are the third largest in the world other than China and the largest company in India at 137.5 million tons. And very fast, we'll be reaching 200 million tons. And we are the only company in the world who has sold 100 million tons. So, you know, being so many firsts in the country and in the global arena, we don't call ourselves a cement company per se. We call ourselves a building solutions company. Because we feel that the pitch, the entire pitch is not only on quality but on the customer. And a customer needs a solution. Any customer, he or she doesn't actually look for a product. He or she looks at a solution. And that solution should happen at every stage of home building or any construction per se. So we have identified various stages of construction. You know, for a normal, simple home building, there are 14 stages. Starting from, planning, estimating, site selection, and then the construction starts. So previously, we used to intervene or engage at the construction stage, where you need cement. We are talking about IS 4, 5, 6 and all. We also participate in these discussions. But cement was our forte. But today, we have a series of not only products but solutions throughout the stages, along the value chain, the construction value chain. So, it's not only cement that we offer or value-added cements, like, we are talking about IS codes. We also talk about, augmented products like LC3, limestone calcined clay cement. We are coming out with that very soon. We have started the composite cement. So all these value-added products, those are buying in now ternary blends, where you may need supplementary SCMs also. So we are only talking about value-add solutions to customers throughout the journey of home building or any construction per se. So I think this is not getting fixed. So I just narrate it instead of ये ठीक होगा क्या? If you are not getting fixed, I'll just run through. And also with the paucities of some time. So UltraTech today, as on date, we have a market cap of 2 lakh crore. I mean, that's a huge number. So let's talk in terms of capacity. 137.5 million tons. We have around 62 plants, about 25 integrated plants, rest grinding units and bulk terminals, spread all over the country, also in the UAE, in Sri Lanka. So we have spread our wings beyond also. Our vision and mission, if you say, to be the leaders in building solutions. We are not talking about to be the largest cement company. We are the largest cement company. But our vision is to be the leaders in building solution based on 4 pillars of, the 4 pillars are innovation, customer centricity, which is a very, very core area for us, customer centricity, innovation, team empowerment, and sustainability. So we live by these mantras, by the mission and vision. Okay. You full screen kare? You're showing it from that screen. So now, India is number 1 cement. Nothing. It's not a though rocket science. I mean, and we are far ahead of the second competition. They are at 67, 68 million tons, and we are more than double that capacity. Go ahead. And Aditya Birla Group, as it's a very big corporate, we are very proud. So we are in fashion, Aditya Birla Fashion. We are in retail. We are in, Vodafone VI, Vodafone Idea, and all that. So there are a lot of other businesses which Aditya Birla can boast of, and many of them are world's number 1 or number 2. So it's a huge group. Our head office or the corporate office is very close to this place at Worli, at the Aditya Birla Center. And we operate the cement HO, we operate from Aura Center in Andheri, East. Next. So this is how we are positioned. We have 23 integrated plants. You can see 8 bulk terminals, 29 grinding units, a few more jetties, not one, a few more have added. And we have a white cement plant. The largest white cement plant also belongs to Ultratech, that's the Birla White. And of course, we also have the largest RMC production in the country, having more than 300 plus plants. Apart from this, we are touching the life through our CSR programs of more than 1.3 million people. Let me also give you some more information. Every month, we are engaging with more than 4 lakh individual home builders who are building their houses. We have an association with more than 29 lakh mason contractors across the country. There are about 80,000 plus dealers for Ultratech across India. And we are also actively connected at any given point of time, every month you can say, of more than 50,000 architects and engineers. That also pan India. So that is the reach that we have, that is the connect or engagement that we have. Next please. So the leader in building solutions, and that is our vision. Next. And of course, to build, these are very important words, deliver superior value to our stakeholders. That's always a, that's the thought process. Go next. So this is a journey, 2004, if we take a short span of say 2 decades, from 204 million, in 2004, from 31 million, we have come to 137.85 billion. So the growth has been manifold. Well, it's more than 200%, but that's how the company has that accelerated growth, and that has all happened not only because of our mission and vision of the changes or the agility that we have or the quality superiority that we have, but also because of the support and the patronage that we have received from all practicing professionals like you. And I think we should always remain, we should never forget that you have brought us here today. Next. So these are just, so as I said, that we have that proud privilege to be the only company in the world who have actually sold 100 million tons in a year, which was last year. This year we are planning to sell around 140 to 150 million tons. Next. And as I said, the basket, it's not only cement, of course cement is our core with 137 or 140 million odd tons, but then we have a Ultratech Building Solutions. That's also a concept. More than 3,000 stores we have across the country, which is a one-stop building shop. So it's a air-conditioned signature sort of a shop. It doesn't look like a cement shop or the mom and a pop shop that they call normally. It's a proper designer shop, air-conditioned, well-decked. You have a place to sit. There is a gallery and everything: cement, paints, reinforcements, plumbing items, sanitary items, everything is available there. So it's a one-stop solution for home building, you can say. We have a downstream products, building products. We have solutions now. We are talking about solutions. We are not talking about products like waterproofing solutions, flooring solutions, tiling solutions, grouting solutions, so on and so forth. And then, of course, as I said, the augmented products we have. The ready-mix concrete, we are the largest in RMC in the country. Then, of course, we have also brought in our engaging app, as I was saying, that now, our approach is not physical. Our approach is not only digital, our approach is digital. So we connect, every month, as I said, we connect with, say, 5 lakh people physically, and maybe another 5 lakh people digitally. So that sort of through an app, which is the UTech app that it's pretty well known now, it's getting good acceptance, where we have focus on a site. There is a site, say anybody is having his construction site, his or her construction site. So stage-wise, we have the focus, we have the engagement at every stage, foundation stage, beam column stage, slab stage, every stage, post-construction, these 14 stages, show you those 14 stages. Plus, who are the other stakeholders? contractor, engineer, architect, what is their progress, everything is available and everybody can engage with everybody. So that sort of a platform, that sort of a networking within the ecosystem, that also we have built in through a digital app, which is the UTech app. Very interesting. I mean, time is not enough, but one day I would advise and request my team members to come to you and tell you or take you through or walk you through that app. Next. So now we are also talking about green advantage. Green is the new mantra. So all our products, or most of our products, have a Green Pro certification. Plus, we are working a lot towards with the IGB for the IGBC certification. There are several homes already where we have provided the IGBC certification. Of course, in collaboration with Griha or some agency. So, and of course we have the very amazing concrete, the value-added concrete per se, like for ultra-high performance concrete, decorative concrete. In Ayodhya, the temple which was recently inaugurated by the Honorable Prime Minister, about 16.5 kilometers of the Rampath, and there's another road, 16.5 kilometers plus another 2.5 kilometers, about 20 kilometers, 19-20 kilometers, where our stamped concrete has been used. The entire floor has been used by UltraTech stamped concrete. In the recently opened Parliament building, the new Parliament building, Central Vista, more than 1 lakh square meters of spray plaster has been used, the new technology, again through UltraTech. So all the iconic projects, we are there. With all the home builders, across the stages, we are there. So that way UltraTech has been present everywhere in all the spaces. So going forward, next. So these are some of the different products, Next. And of course, as I said, that the building products, we are there in all the categories, like repair, rehabilitation, plaster, mortar, grouting, flooring, AC blocks, flooring, floor screens, so on and so forth. Next. And of course, the concrete solutions. We have solutions like structural solutions, durability solutions, decorative concrete, floor and slab solutions, and of course, the repair. This product, ZIP, it's a DIY product, do-it-yourself product. You can just buy it, fix it. You don't need an applicator. So we are trying to make life simple also for application. Next. And of course, for critical constructions, like we call them the VAC or the VAC plus, value-added concrete per se. Decor, you can see, as I said, which they have used in Ayodhya. The I-floors for the factories, lightweight concrete, ZIP, that DIY. Aqua Seal, that's the waterproofing stuff. Free flow, it's a self-compacting concrete. Then we have the rapid, where you need very high strength. BMCs are using rapid in some of the applications because they need to, decongest the road. We need to move out of the site because the road has to be operational. We cannot block the road for a long time for repair. And of course, thermocol. And now we have facades also, which is the UHPC. Facades, architects are very much interested. You can make those designs. So we call it the Ultra Facade. That's a very good product made through M80, M100 UHPC. It's ultra high performance concrete. Next. And the services, just give you, I'll take another minute maximum. We have this mobile van. We are the pioneers, and I would say it was the first concept was Jain Saab who is sitting here. So I tell people, sir, you are here, that you had started this concept and now it is adopted by all cement companies across the country. We have at this moment 400 mobile concrete labs across the country. This itself is a mobile, center of excellence. It reaches out to the site. It's sort of a door delivery, reaches out to the site and provides all sorts of services like, concrete testing, like Q testing, NDT, sill testing, all that you need at the site to add value to the concrete and to construction. And of course, we have the entire solution, as I said. We also have a VR film loaded in this van, so that can also be shown. We have this facility also, through the UTech, we provide virtual reality experience. The person who is building his or her house, maybe before construction, we take them on a journey through the Oculus set. There is a VR, we have VR set about 100 VR centers across the country, virtual reality centers or experience centers. Even we sometimes send it to the mobile van where the Oculus and the laptop is set, and anybody wants to have an experience of his or her house, how it is going to feel. It is an immersive and an engaging experience about the look and feel of that house which is not built. So through the 3D virtual reality, we give that experience. So that is also provided to this van. So a lot of things, a lot of demonstrations we do. So it's a real value add when this van reaches out to any site for that matter. Next. Construction, value chain into the 14 stages. At every stage, we have a product or a service and a solution. At every stage, and the stages start from block finalization, home planning. So we were previously, that's the change that has happened, we were only into the construction stage after the excavation and foundation work starts. But now, plot finalization, what are the permissions required, what is the budgeting required, planning, vastu, expert search, everything is available in the app. Then we have the excavation foundation where we can intervene with our BPD products, with our liquid, with our RMC products, ready-mix concrete products, and with cement. Then the plane, column, beam, slab. So all the stages have been, identified, and all products, services, solutions are, tailor-made, are available for these stages. Next. This is how the output sees through the EUTech app basically. What are the these are some of the posters that we have provided basically. And of course some of the national projects, apart from all the metros and the Moteras in Gujarat, or the Statue of Unity, and the Central Vista, and now the Ram Temple, and the Atal Tunnel, and now we are going to Pune through the the coastal road also, just to have a look where UltraTech has been involved in a very major way. So I think everywhere, all iconic structures across the country, I think UltraTech is present. Next. And of course, these are our valued customers, apart from, about 30-35 lakh home builders per year in the country. Apart from 10-12 lakh mason contractors, because they are actively involved. We have a group of, say, 29-30 lakh mason contractors, about 10-12 mason contractors who are actively involved. These are also some of the very big project authorities who are actively involved in this. That's it. So thank you for your time, for listening to us and giving us this opportunity. Thank you.
Thank you, Sankarji, for your beautiful presentation of all the products of UltraTech and various solutions and services of UltraTech Cements. So thank you, the team of UltraTech. Now there is one announcement. Now you are waiting for the lunch. Lunch is arranged just at the left side of the corridor, at the end near computer engineering department. There is open space, so lunch is arranged. All are requested to join for the lunch, and our next session will start sharp at 2 o'clock. So all are requested to join on time. Thank you.
And announcement is Mr. Jain Kulkarni has announced a donation to ISSE 1.25 lakhs. So big applause for Mr. Jain Kulkarni. And all our well-wishers, I appeal those who wish to go for ISSE, you are welcome in any form. You can share your experience for our technical journal. You can participate in our activities. You can of course donate generously to ISSE. So that is my appeal to you. Thank you very much.
So after a delicious lunch, we now start with the technical session number 2. This session starts with the presentation on pre-draft IS 13935, and it will be explained by Engineer Jaswant Arlekar sir. Brief introduction of Arlekar sir. Jaswant N. Arlekar is a practicing civil engineer and structural engineer, and an adjunct professor at the National Center of Disaster Mitigation and Management, Malviya National Institute of Technology, Jaipur. He holds a PhD from IIT Kanpur. With a professional experience, practice, research and teaching of over 20 years, he has conducted short courses on subject of analysis, design and detailing of structural steel. He has designed and executed several residential, commercial, public, auditoriums and industrial projects in reinforced concrete and structural steel. He also has experience in assessment, repair and retrofit of structures with a special emphasis on earthquake-related safety. He is a member of Code Committee of Bureau of Indian Standards and Indian Road Congress. So now I request Arlekar sir to take charge of the mic and start the presentation.
Thank you. Welcome back. Thank you. I hope you've had a good lunch because I've been given 1 hour to do this. Actually, I need 2. So we'll try to finish it in 1. Let's see how much time I take. So, in terms of doing this, as said, Professor Murthy was supposed to come for this, but unfortunately there's some emergency. I know you are expecting Professor Murthy to do this, but please listen to me. Maybe I won't be Professor Murthy, but I'll try to do some justice to this. Okay, the main agenda of doing this was, like in the morning Professor Goswami explained, we have 3 verticals in our code. 1893, which addresses the hazard, the loading and the analysis part. 13920, the detailing and design part. And then there is this 13935, this is a new number that has come. But this is basically going to address all our existing buildings, the existing stock of housing which is there in India. How to take care of them, because it's, as structural engineers here, you would appreciate that demolishing a building after 50 years is not a possibility that we look forward to. Anybody will not allow you to do that. We have, in this city itself, buildings which are much more than 50 years. So we need to have some methodology, we need to have some way of making sure that this building can be extended, the life can be extended. Before that, we need to assess and see what is the way to find out what is the potential of the building to extend the life. If not, how to retrofit them. So this is the code that is going to look at this aspect where we assess the building, repair the building, retrofit the building, and do the overall evaluation, say that okay, this building is okay to extend the life. Just go with a few pictures that I have collected over a few years. 10 years fire brigade got 3,000 plus calls in about 10 years for building collapse, not because of earthquake. This is only in Mumbai. In the last 10 years, we have not had any earthquake which would collapse the building. So we have a problem of buildings not, they just collapse. We know, I mean, all of you are aware of some buildings which are just going down. So as per the requirement, there are about 15,000 buildings in the island city, and with the current speed and with the current know-how of redeveloping and the current capacity that we have, it will take about 200 years. This is an article in Times of India in 2021. So it's not a solution. Redeveloping a building or the buildings, the stock of buildings that we have is not a solution. So we need to figure out a way of, so we do have a way of doing it. We do structural audits of building. How we do it, what is the rigor that is involved, that is the next level that we go. We do have a system of taking care of such buildings. And structural audits and repairs should be an interim measure to ensure life safety of such buildings. Another pictorial which shows what was the problem with this building. I don't want to talk about this. Earlier it was fine. Yeah. better. So the message that we are taking from this, most of our buildings which are 15,000 stock that we are talking about are not in very good conditions. They are, from medium, moderate to poor condition type of a situation. So the solution that we are talking about is how to assess them, how to retrofit them. Another pictorial similar, 2021 August, there was a mass evacuation of 4 or 5 buildings in Ulhasnagar which were about to collapse. People were taken out, no lives were lost in this. But earlier, before this, there were some people who lost their lives. This another picture, nobody died in this. Unfortunately, this Mr. Sundar Shaw was standing on the pavement, the building collapsed. He was not a resident of the building. So, unfortunate, very unlucky. So, interim solution, we look at, how to ensure life safety of the residents and overall safety of the building through structural audit and repairs. We need to understand how to assess the building and repair. Some more pictures which I have collected. I'll run through this very quickly. Oh. Excuse me. Able to use. So, just basics of structural engineering and earthquake design. So, we look at design loads which are force loads, then there are displacement loads. This we understand very well. The people who are here will understand this very well. Force loads are dead loads, imposed loads, wind loads, snow loads. All the loads which actually apply a force on a building. This light is actually disturbing. ये light थोड़ा dim करना है. Impact load, construction load, pre-stressing. These are all force-based load. In parallel to that are displacement load, particularly the earthquake load that we are worried about or we are concerned with. In addition to that, there are temperature creep, shrinkage, elastic shortening, foundation settlement. And earthquake load is one that we are looking at, and this code is going to be focused on assessment of earthquake loads and their effects on the building. So quickly, what is an earthquake? It's a ground motion, it's energy release, waves travel, they come up to the surface, they affect our structure because the ground is moving. So movement of the ground translates into movement of the building because of inertial effects, and that is how deformation happens in the building, and that is how the force is generated, that is how the building gets damaged. So when there is an earthquake, ground moves, there's deformation because of the inertial action caused by the acceleration in the ground. So when you look at force displacement, in minor earthquake, there's some force that comes in the building. In a moderate earthquake, slightly higher force. In severe earthquake, larger displacement because the structure is going into some kind of inelastic behavior or some damage in the structure. And that's how the load displacement curve is drawn, or this is the behavior of the structure. So there are three levels of earthquakes that we need to consider usually: minor, moderate, and severe. In severe, we will expect a lot of damage in the structure, and moderate earthquake, little damage. In small earthquakes, we should not expect any damage. It should we should be able to use the structure very quickly and come back and continue with our business. Earthquake versus wind, like I explained. Wind is a force-based loading on the structure. It's a force physically applied by the movement of the wind. Because the structure is blocking it, the force gets created on the structure. But earthquake is not like that. Earthquake is a movement of the ground. Because of inertia, there's deformation in the structure. And that is how the forces are created. Because one column, 2 points of the column are going in the opposite direction. That is how forces are generated in those structural members. So if you look at wind-based loading, this is an everyday load, almost everyday load. Earthquake will happen once, maybe twice, or maybe never in the life of the structure. So there is a probabilistic assessment in the earthquake saying that, like in the morning we were discussing return periods of earthquake. That is how we assess the earthquake. We don't design the earthquake for the full load, we design for a lower load because we expect damage in the structure. Because of the damage, it's a reduced load that is coming in the structure. So wind load is a force base, that's the green part of the thing, where we have the stiffness of the structure, and because of the stiffness, that is forces applied on it, those are the forces which are generated, the reactions of the force that is applied generated in the structural members, and we design for them. Straightforward, very easy to understand. But earthquake is deformation applied. Because of the deformation, there is some change in the structure, and corresponding to that, we say this is the equivalent force that can be generated in the structure, and we design it for that structure. So it's basically deformation, structure moves, and we say this is the equivalent force in the structure. So that's how the design is categorized, force-based design and deformation design. So when we talk about, we've seen this in the morning, 7 virtues that we look at. One is the configuration, we make the structure good. All the good things of the structure, good column, good spacing of the column, good grid, good material, good construction practices, no irregularities. That's the configuration of the structure. Start with a good structure. Then you provide minimum stiffness in the structure. Minimum stiffness required, which is code based. Then you have minimum level of strength. That is like whatever the code says, the PP is the minimum force that you have to design for. That's not the force you have to design. You can design for a higher also. Then there is ductility. Because of the damage that is coming in the structure, while the structure is getting damaged with the earthquake force, the structure should not collapse. So primary goal that we are trying to achieve is the structure can sustain damage in an earthquake, but it should not collapse. So collapse of the structure is basically a prohibited thing. So don't let the structure collapse. Let there be maximum damage in the structure. You walk out. In the morning, director VJTI said he experienced some earthquake in Guwahati. They were shaking in the middle of the night. They walked out the structure and they went on the road and stood. That is the kind of status that we have to achieve. Shaking in the structure, even major damage, but no life fatalities. So life safety is the prime objective that we are looking at. Then along with ductility, deformability, because the movement is there, the structure should be able to deform to a certain extent without collapsing. And this can be complemented with a desired collapse mechanism. You say that only specific parts of the structure will sustain damage. Like in the beam, at the ends of the beam near the column, there will be some kind of damage that will happen. That will help us in dissipating the energy that is fed by the earthquake. Or you have other places and not in the column. Like if you have a plastic hinge in the column or hinge in the column, the structure will collapse very quickly. So place the hinges in the beams. That is how the code also addresses. This code tells us to do a strong column, weak beam design in case of buildings, where the columns are very strong, the plastic hinge or damage happens only in the beam, the collapse probability is much lesser and it can sustain much more deformation, much more energy dissipation can be applied. And the 7th virtue is the energy that we are able to dissipate when the structure has been subjected to an earthquake. So, repeating, 3, strength, configuration, stiffness and strength, minimum, good configuration, minimum stiffness, minimum strength, then ductility and deformation, because we are expecting damage in an earthquake, it should be able to deform, and the ductility of the members will be giving that deformation capacity to the building. For assessing this, we'll need some type of nonlinear analysis. Right now, the first 3, 1, 2, 3 are we are able to achieve 1, 2, 3 based on the elastic design. elastic analysis, but 2 and 3 to assess and say that yes, this structure has these 2 features, we'll need some kind of nonlinear analysis. Collapse mechanism, like we said, strong column, weak beam, is a provision that is given in the code. It's a prescriptive provision, but to say that yes, this structure is able to achieve that goal of strong column, weak beam, is the collapse mechanism that we assess the structure, do some kind of analysis. And then the next stage would be, as a follow stage, would be to see what is the energy dissipation capacity of the structure. So this 7 virtues. So when we have earthquakes, we have column structure and we have wall structure. We know, and through experience, through analysis, through a lot of design that people have done, walls are able to sustain larger deformation. Columns will be able to take higher load, but walls will be able to take higher load as well as a lot of deformation capacity, which will be available. Like, that's why we are trying to push, or the earthquake codes that are coming in the country now are trying to push towards wall construction rather than just moment resisting frame with columns and beams, particularly to achieve the deformation capacity, which will be based on the ductility that you achieved in the structure. So the minimum is lateral stiffness, overall strength, and deformability. These are the 3 things that we need to do, and we are currently actually trying to do that. And if we design as per the code, we think that we'll be able to achieve all these 3 aspects that are required by the code. So with this background of earthquake behavior and analysis and the design, we see what is required for earthquake safety assessment. To retrofit a structure, we need to first understand what the structure is capable of, do the assessment, some analysis, some preliminary design, some, what is the configuration of structure. All those put together, we come up with a plan of whether the structure is okay or not okay. If not okay, what is the next step to be done? Some nomenclature, I'll just explain. Retrofit, remodel, and repair. These are the 3 things. I'm sure none of us are confused with this, I just want to put it out there. Retrofit is basically where you strengthen the structure. Your retro is like previous and then you fit it. Remodeling is changing in the configuration, and repair is repair. If something is wrong, if there's a crack, you open it up, repair it. So in retrofit, you basically increase the structural capacity. You look at the structural capacity and check its adequacy, and if not adequate, then you improve it. Remodeling is functional change in the structure. You check out some walls, check out some beams, add some walls. So that kind of a repair. And they may not be structural, but remodeling will also include non-structural changes to the building. Repair is just visual improvement. Painting, repair of plasters, or some spalling of concrete has happened, you put the reinforcement back, do some kind of drilling, and repair the structure. So basically, visual improvement is basically correlated to repair. Most of the buildings that we see which are being repaired, this is the 3rd part that is getting done, where we just restore the structure back to its original condition, the existing condition, and there is no increase in structural capacity. So in the retrofit, there are 3 again. Restoration retrofit, where you bring back the structure to its original capacity. Then there's an upgrade, you increase its capacity. It can take a larger earthquake, can take higher forces, can take higher load. And then there's a rearrangement in structural capacity, where you say that, okay, this structure is not capable in the current configuration. I'm not able to upgrade it, nor I'm able to restore it, but I need to make some structural configuration. You add some members, you add braces, or you add structural walls, or you add buttresses in the structure. That is the rearrangement that will happen. And in rearrangement, sometimes we downgrade the structure also. Like there are many bridges which exist across internationally, where they downgrade the class of load that the bridge is capable of taking on. So that is another method of increasing the life of the sustainability model, where you say you don't load the structure to that level, lower the loading, now the structure is okay to take that load. But remember, retrofit and repair are not synonymous. Repair is repair, it's visual, and retrofit is adding strength to the structure by these 3 methods, where restore, upgrade, or rearrange. So we are improving the structure. One is increasing its capacity, and in rearranging or in reducing the capacity, we reduce the capacity. So if the capacity cannot come up to that level, we reduce the demand on the structure and bring them at par. So quickly go through what current practice is in Mumbai, across the country also. Condition assessment is done. We do visual assessment. We look at all the cracks, repairs, leakages, spalling of concrete, exposure of reinforcement. Do some structural identification. Many times the drawings are not available. We have some drawings available. We identify which is the column, which is the beam, what is the size of the beam, what is the size of the column. We do some kind of non-destructive testing, destructive testing, and identify what is the material. Again, maybe do some assumptions and say, okay, this is the structure right now, and what do I do for the repair of the structure? We go back and the most of the effort here is to restore the structure to its current condition. Whatever the condition it was maybe 6 months ago, 1 year, 2 years ago, we restore it by taking out bad concrete, we replace it with some polymer concrete or mortar or maybe micro concrete type of thing. Or if the reinforcement is corroded, we replace that reinforcement with the best method that we have. We replace this reinforcement and say that this size is same, reinforcement has come back to its original number, and now the structure is okay, it is okay as per the existing condition, existing design it was there. That was the current existing practice. In the desired practice, what all of us want, I mean, I can say this for all the structural engineers here, that this is the minimum required. Most of us are doing this. The next level is to actually go back to the structure after getting all the information, making assumptions, all the information that you have. Let us say we have 80% of the information, we go back and perform a structural analysis. We check the configuration, update the loading, check the structural design of the existing structure. With all your experience, all your assumptions, all the knowledge that you have collected about the structure, whether it is through drawings or I'm sorry, okay. The charge is gone. So we were talking about the current practice, and then we are looking at what the desired practice should be. We look at the structure, we do all the assumptions, we get all the information, we make our judgment calls about loading, configuration of the structure, the structural member sizes, reinforcement, everything. We make an assumption. Let's say we are at a stage where we understand the structure, sort of understand the structure. Then it comes back to your original design, I mean new building design. You have the structure, now you have to design and check whether the structure is okay for all the requirements and the structural behavior. So structural analysis using configuration of the structure and updated loading, because we want to qualify the structure for the current loading system, whatever the current codes are saying. Then check the structural design for performance, evaluate the performance of the structure as per the standard and say whether the structure is okay or not, and then go into construction and do the structural upgrade. So that is what we desire, that is what we want now. The top part that we are doing, and this obviously comes with certification like it does for the new buildings. At the end of the building of the new structure, we have to certify that the design is adequate as per the code, and we take responsibility for the design. Similar thing is expected here also, where we do the structural analysis, structural design, structural construction, and say that this is okay for occupation now. So that is what the desired practice should be. So when you look at new structures, you estimate the load, analyze the structure, design in detail, and then construct. It's top-down process, simple process. We make all the assumption and we implement it and achieve the structure that we want to have. But it's not the process standards that are familiar to this process, these are the standards that we use. Construction, there are many standards of construction. quality of construction, management of construction. So those are the standards which are used by the construction industry. But if you look at the existing structures, we have to assess it first. We have to understand what is the existing condition of the structure, what is the existing configuration of the structure, what is the capability of the structure. That comes as assessment. And then combined with analysis, we go back and evaluate for adequacy. We do assessment, analysis and design, and then we evaluate, say that this is adequate as per the relevant standards. And that is the reverse process, where you already are given a structure and you say whether it's okay or not, and then do some kind of intervention. So again, just revising this: configuration, stiffness, minimum strength, ductility, which comes along with deformability, desired collapse mechanism, and energy cell. This was shown earlier in the morning also. I want to go through this again and again, because this, if you understand this, it will be easier to conceptualize and imagine a structure having all this feature, or whether the structure has a few of this feature, and how to bring this feature to the structure would be easier for the structural engineer. So when we look at retrofit, that's the original design. Damaged state of the structure would be reduced. Both the strength as well as the deformation capability of the structure will be damaged. And if we are able to achieve the retrofit of the, that is the curve that will come, where we restore the structure to its original configuration based on what it was designed for. But there's one small change in this that I would like to state. We have to see how to come to that. The original structure was designed about 50-60 years ago. At that point in whatever the standards were, now the standards have changed substantially. Whether we bring the standards into the picture or not is the question that we need to collectively answer. Then we have retrofit in terms of upgrade, where we have original damage, and the retrofit in terms of upgrade, the nomenclature that we talked about. The top curve, where the increase, there is an increase in the structural strength as well as the structural deformation capacity. Then there is this remodeling, original structure, damaged structure. Remodel will be somewhere in between. We make some changes, and based on our understanding of behavior of the structure and the loading, we say that slight increase we may be able to achieve. We look at repair. In repair, we are actually going back to its original configuration. You achieve at the damage stage, if you just take out plaster, if you just take out cover concrete and replace it mortar or micro concrete, you are not going to add any value to it. You are going to restore its damaged state. Just visually you will be able to say this is looking good, the beam is good, but you have not done the due diligence of assessing and checking the structure whether it is capable of taking the expected loads or not. So if you look at all those three together, a retrofit, upgrade, retrofit, restore, remodel and repair, this is the levels that we will achieve in terms of how the structure is going to serve us for the remaining life of, for its remaining life. So when we look at another pictorial, we're trying to basically put in different ways of understanding what this process of assessing and retrofit entails. This is the normal life of the structure, and if there are all these deteriorating characteristics which are imposed on the structure, where there is sulfate, HI, carbonation, concrete, then some damage, bad use, leakage, corrosion, all those, then you have the behavior of the structure would be like this. The damage would occur very quickly in a shorter time, and damage will mount on to, the increase in damage would be the third curve that I've shown there in red. So normal life of the structure without all these problems is what we're expecting, but with these in picture, we'll have a problem of how to then make the structure livable, then make the structure safe to live in. So that gives the reduced life of the structure from the normal to back based on whatever kind of environmental factors are affecting the structure. So if you look at the behavior of the structure, if you have a capacity of the structure which is degrading over time, life as in time, and the capacity of the structure, if you at some point in time say that I want to do a restoration, retrofit or upgrade or one of those, then if you do it earlier, you may be able to extend the life of the structure by a little bit. If you do a late retrofit, because the structure has gone down so much, getting in all those features of the structure compounded with the new standards, we may not be able to achieve the extension in the life of the structure. It's not that we will not be able to achieve, but the difficulty level will be higher. The effort that we need to put in, the money that we have to spend would be much larger when we do a late retrofit. So combining this together, there are two pictures that are drawn here. Performance of the building at different levels, target limit, service limit and safety limit. So if you do an intervention, a repair or retrofit at some point in time, you increase the life of the structure, and the structure now is brought back to its good state where it can take sustained loads. But at a certain time of the structure where it's highly degraded, going in for retrofit is going to be more and more difficult. The second picture on the right hand side, we are trying to show if you do periodic maintenance, which will cost less. It's not a big chunk of money that is required at one point in time. You do periodic maintenance, you may be able to extend the life of the structure for a very large, for a longer period, but keeping the level or the health of the structure at a higher level rather than coming down and doing a one-time retrofit, which may not be so easily possible. So another pictorial where we say how the structure behaves. If you go in for repair, you are actually just restoring the structure at its current level. There is no added value in terms of behavior of the structure or the capacity of the structure. So there's no improvement. In case of the design load, the structure will not be able to perform the way it is supposed to perform. So again, saying that structural repair is not structural retrofit. So we have to come out of this, that if you just do some kind of restoration repair, it amounts to a retrofit of the structure. So we right now don't have a compiled document, or we don't have compiled guidance which tells us how to do this. The effort of BIS CED 39 is to create a document which will be able to guide us in taking this forward. So when we are looking at restoration, we are looking at upgrade, we are looking at remodeling, or when we are looking at retrofit. Why are we doing this? Because there is some deficiency that is there originally in the structure, or something has happened to the structure where the structural capacity has degraded. Either it is the environmental conditions that we looked at, or the change in codal provisions, or one where we say insufficient load combinations considered. So you would have under-designed the beam, or you have bad connection. The connections are not designed. Strong column, weak beam has not been followed. That means because of the way the structure behaves during an earthquake shaking. And then there's large deformation because of this L shape at the ends. And we need to see how to avoid this and how to take care of. If not, then how to take care of this. And we do have structure like this right here in this city, which is like a plus-shaped structure. This is one structure in Goregaon, where it's not on a hill, but it has a plus shape. So in this point, basically the stress concentration would come in. Then we have the effects of the entrant corner. This is very well captured in this literature. Some concepts of earthquake resistant behavior of building. This book is written by C.V.R. Murthy and Rupin Goswami. They have covered various configurations that we should look out for, and they have shown pictorial representation of what happens if this is the type of structure. Like if you see in this, because of this type of deformation, there's a stress concentration at the joints or the re-entrant corners. Then we have irregular geometries. This is again covered in the code. What is to be done with this is also given the current draft of the code. Earlier code was also talking about it very subtly, it was talking about. But now the revised code that is coming out is explicitly talking about how to take care of this and how to avoid this. And at what level you have to say that this is not allowed, this is prohibited. So these are the problem points in these types of buildings. At the re-entrant, wherever there is a change in geometry is the problem basically. So it's a very layman type of terms if you use. Wherever there's a change in geometry, change in shape, would have a problem with the re-entrant corner. This is a famous building in Bombay. This is the typewriter building, which basically is the stepped building that the code talks about. So this is another building, which is basically the inverted building. So there are 3 plus 3, 9 columns at the base, and then there are cantilevers which are coming out by about 7 meters. So this is a typical case that has been covered in our code actually. So we have this irregularities, what happens when we have such a configuration. It's explained in this book. What would be the condition of the structure if a design level earthquake strikes. So if you get if you have the time, this book is freely available on the internet. You should go through this, and it gives a lot of insight into what behavior is and how to avoid such behaviors. Then we have open ground story, which is a traditional problem building for us across the country. We have seen this in many of the earthquakes has seen this, whether it's Bhuj or Chamoli or even Jabalpur earthquake, and even before that in the Kilario. In some cases of open ground story, weak story was noticed, and we have been struggling with this problem, how to avoid this and how to make our buildings safe when these conditions exist. In tall structures, you would have this service stores, which may be a problem of weak story or open story. How to deal with them is one of the things that most of the structural engineer would struggle with. Then we have open ground story, we have weak stories, and then we have stories with infills, without infills, weak and open. So these are the configurations that are being covered in the code now. Weak and flexible story, and reduced column sizes. This is a very common practice that as we go higher up, the load is reducing, so we reduce the column size. It's a natural thing for a engineer to do, but we have to see that there's drastic changes are not happening in those structures. So this is a typical example of an open ground story, because if you want to park a car, this is all parking area, and that is how the open ground story comes into the picture. This is a picture from a Jabalpur earthquake, where we noticed this for the first time. First time in India, a building which was an open ground story was subject to an earthquake, and we were able to look at it and understand what is the behavior. Theoretical knowledge before that was there in India, but we looked at this and we then came up with strategies of avoiding this, or doing an intervention which would reduce the effects of open ground story. So again, structural deficiencies, open ground story. The book that I talked about explains what are the effects, and pictorially they have tried to explain what will happen if this is the condition that you have. And then later in the book they also try to explain what are the methods that you should have. This is a weak story at the upper level. And irregular mass distribution. Again, heavy mass at different levels. This is possible in many of the buildings where you have a service floor which is having larger weight or mass which is there. So these will be the problem points in the building. Then we have irregular plan configuration, irregular mass distribution. So this is just a tip of the iceberg of what are the problems that can happen. Now, having knowledge of this, these are the problems that we have to deal with. Based on that, we go into the next step of identifying, and once we know what are the problems, we would be able to spot them and pinpoint them and say, okay, this is the problem, this is the solution that I want to have. So what are the options that we have available for retrofitting of a building now, or improving, upgrading, remodeling, all those 4 terms that we use. Basically, member retrofitting, where we do jacketing, wrapping, column jacketing, beam jacketing. Then we have structural retrofitting, where we add structural components, columns, beams, walls, into the existing structure. And there's material level retrofitting, where we add some material into the beam and strengthen it. Like epoxy grouting is one of the very common solution that is used everywhere, where you pump in some epoxy kind of compound and say that the strength of that has increased. So this is a common where we do jacketing of the column, remove the cover, put additional reinforcement and reconcrete it. This red is the original column, and the one outside is the new column that has been added, new jacket. The increase in size of the column is there. Then when there is a damaged portion, you can add reinforcement to the column and do a jacketing. So these are traditional standard methods that are being practiced across the country, where increase in size of the member, increase in strength of the member is possible. Here also, existing beam and a slab with existing the reinforcement of the column beam is not shown. When you add a jacket around it, you can do it like this. It's a very tedious and involved process. It takes a lot of time, and how to assess this, how to do an analysis of this, also a question. I mean, we don't understand this, how to do this, but such a large stock of buildings which are inadequate right now. These are the methods that are available for us. Then addition of new RC wall. We have to connect the walls with the members of the building, maybe the column foundation, create new foundation connected with the beam. And then this is the existing structure, and this is the new structure that is added to take care of the lateral load that is going to be subjected to. Then there is a method of adding masonry walls also, and this was practiced by many people. It was recommended also. Just go and add brick masonry walls in all the open ground, so just immediately after the Bhuj earthquake. And it is believed that this saved a few collapses of the building in the aftermath of the earthquake and then aftershocks of the earthquake. Original structure, and then you add infill walls, which basically adds a little bit of strength and stiffness to the structure. Then this is very rarely practiced, where you add an additional component, an additional member outside the building. This is an existing building, you add a buttress wall outside the building. May not be very easily possible, but it's another method where you have space and where you have the luxury of encroaching away from the building. This could be another method where we can add lateral stiffness and strength to the building. Then this is commonly practiced across the world. India, few people are practicing this, where you add a cross brace in steel between the joints of the building, the panel of the building. This similar effect as the infill walls or the RC walls, but then in terms of having retrofitting, this is one of the repair techniques that is available. Then another practice that people have, they wrap this carbon fiber wrap to a column or a beam and increase the confinement, and that is able to increase the compression capacity of a member. So traditional methods, there may be many more which I have not covered. I mean, many engineers do different things, and they are able to come up with new methods which may not have been covered here. So we're looking at the pre-draft of 13935, third vertical column of the harmonization of the code, where we are looking at how to assess, repair and strengthen the buildings. This is the sample. This is not in the public domain right now. We are still discussing about this. Right now we have made a draft of the part 1, which is general provision for all structures. Like 13920 and like 1893, we will have different parts for different types of buildings, like for masonry buildings, RCC buildings, steel buildings, and all the other buildings that will come. Maybe bridges will also be covered in this. So looking at earthquake assessment of the structure, we have two types of assessment that we can think of. Pre-earthquake, no earthquakes happened, and the post-earthquake. Post-earthquake has been done after the earthquake. Some of us would be able to visit earthquake damaged sites, but most of us will not get an opportunity to go into an earthquake damaged site. But pre-earthquake, what is to be done? Again, look at all the configurations of the building which are bad, which are good, and based on that try to assess whether this structure is good or not, and based on that decide what kind of intervention and what kind of strengthening is required for that type of structure. So this pre-draft is talking about 5 levels of assessment. The first one is rapid, quickly, within maybe 10 minutes, 20 minutes, half an hour, look at the structure from inside, outside, whatever is possible, and say whether there are major deficiencies in the structure, whether there's an open ground story, whether the columns are too small, whether it is sitting on a slope, whether it is on a sandy strata where it is liquefaction is likely. So these type of global features we identify in the structure and say that these are the problems in the structure and list it down. So this is a rapid quantitative assessment, similar to, you must have heard about rapid visual survey, where you cover about 10-15 buildings in a day. A group of 2-3 engineers, 2-3 technicians go and look at it and identify the buildings and say these are the problems with the building. The second is detailed qualitative assessment, where you put numbers to each one of them, each of the deficiencies which are a little more involved, but you need a little more experienced people. Put numbers to each one of them and then rank them. Then these are qualitative. Then the next 3 are quantitative, where you do preliminary quantitative assessment, where you see overall what is the structural safety margin, whether the base shear is okay or not, whether for the vertical loads that are coming on the building, whether the columns, walls, whatever structural system is available is adequate or not. Then we have basic quantitative assessment, where you check the building with respect to the existing codes or standards that you're going to use. And then there is detailed qualitative, where you do structural compliance with the standard with respect to the behavior of the structure. So you look at what behavior will happen in the structure because of these deficiencies, and then when you suggest a retrofit or a repair method, whether that repair method is adequate or not. So these are the 5 levels that we are proposing in the code right now. And based on, so that's how the 5 levels will come: rapid, detailed assessment, preliminary assessment. These are rapid 2 parts, 0 and 1. Preliminary assessment, quantitative here, then basic assessment, detailed assessment. So slightly higher level of effort for each of the levels. So this is qualitative, this is quantitative. So these are quick methods. This will require a little bit of analysis and design experience to do. So we've tried to put this in a form of a flow chart. You do a 0 level, rapid qualitative assessment. You check the critical aspects, prioritize the buildings. Suppose you have 200 buildings. In that, let us say, in this year I want to do 20 buildings. Based on the rank that you get here on the rapid, take up the first 20 buildings and go to the next step. Then do the detailed qualitative assessment of those buildings and come back to this for the next 20 buildings the next year. Because the rank of that building is lower risk to that building. You take the first set first and start doing the work. So detailed qualitative assessment, then check all the earthquake features, assign the numbers to them, and say if the number is more than, let me go to the next slide. So when you assign the numbers to them, it's more than 90, it's a good structure. Then you come to this step here, preliminary quantitative assessment, do the overall check. If it is satisfied, nothing has to be done, structure is okay. If it is not, then you go to the codal provisions and come, and whether it's satisfied, come back and stop. So in this case, if it is between 60 and 90%, something is wrong with the building, do basic evaluation of the structure, the 3rd level evaluation. Check with the code. If it is satisfied, then you can stop. If you have structures not satisfied, then you go to the detailed evaluation. That's the 3rd, 4th level of testing, that evaluation that is happening. And that will happen for the buildings that receive a less than 60% score. That happens. And detailed qualitative assessment. For normal structure, there's one path given. For critical structure, there's another path given, because the main code, the IS 1893, is doing some kind of subdivisions of type of the structure, basically. So in this, you come here and check for code provision, not sufficient, develop a retrofit technique, check whether it's okay, sufficient. If not sufficient, then you have to go back and do this cycle. I mean, this is a design process, basically. For critical structure, you do code provisions and behavior also. You check the behavior of the structure also, check how it will behave before and after the retrofit measures. Come back and check all these features, configuration, strength, stiffness, deformability of the structure and the members, and then see whether it's sufficient or not. Sufficient, then you can stop. If it is not sufficient, go back and do this. So a little bit of iteration is involved there. So quick summary. Rapid visual, identify major deficiencies which are life-threatening. In second, qualitative assessment, all the key features which are there in the structure, you identify a little more detail, where you look at site, where it is sitting, what is the problem with the ground on which it is sitting, the form of the structure, basically configuration, the structural load resisting system, material, and the construction practice or the construction type that has been used, whether it was good or bad. It could be, good construction done, you can improve the grade, the structure's capability much higher. Then preliminary quantitative assessment is a basic check on just lateral loads, whether VB in X direction, VB in Y direction, adequate or not. Based on the understanding of structure, quickly we can calculate what is the base shear, and then go with the capacities which we are able to identify from the standards, and check the design and see whether that's satisfied. The third one is compliance with the standards. Do a detailed analysis of the structure, check all the equilibrium equation laws, constitutive laws, and compatibility. Do the design based on the like when we spoke in the beginning of this presentation, where we make all our assumptions, where we collect all the documents and take leaps of faith and say that this is my structure, assume the reinforcement, all that. After doing all that, we come up with the understanding that the structure can be passed through this kind of an assessment. And then the fourth level, or the fifth level actually, 0 to 4 is the fifth level. We see whether the compliance is there with the code, including the behavior of the structure. So this basically look at the performance and how it will behave, and based on that actually do the assessment of the structure and qualify the structure. So this in a nutshell is what the 13935 is trying to achieve, and that is how the code is being drafted. So outcomes is the answers to what is the structure safe and what and where the deficiencies are. All the critical problems that can happen in the structure, compare them with each other and say that this is a critical structure or not. Even if the structure may not collapse, what level of damage would it sustain given a design level earthquake to occur? And main assessment whether the method is going to give you what you are trying to achieve. So I'll quickly go through this, what rapid visual assessment or rapid qualitative assessment is. You identify the major deficiencies in the building, make on the current housing practices, document all the. So I will not go through this because there are many slides in this. In a nutshell, I'll say you identify good characters in the building. Make a list of that and compare it with the building that you're looking at it. So the building has an open ground story. You say, okay, this is an open ground story. Open ground story is not good. It has a weak story. It's not good. It has a column which is undersized, not good. Mark that as a negative point on that building and go ahead with the assessment. Then these are the features that we look at. Materials, who has constructed it, what are the methods that were used, whether it was good construction, bad construction. And this has to be done for different types of building. One is for the houses, whether it could be masonry houses, could be RC buildings, could be bridges, or it could be steel structures, any type of structure that we have. So we are going to have the same strategy which we are going to have for 1893 and 13920, where we will have the main code and then attachments to the code or subsections to that code of dealing with each of these typologies. Frame structure, truss structure, mixed structure, good and bad comparison, where you say that, okay, this is good, this is not good. And in that, again, you look at structural and non-structural elements, assign ranks for each one of them. If this is the problem, if you have, let's say, a TV or a heavy mass sitting on top, which is likely to slide down and fall and cause life-threatening conditions, then you give a higher level of negative marking to that. So S factors and N factors. So those will be life-threatening and economic losses factor. So in this, we do this. All the good features are listed on one side. Compare it with your building that you're looking at and give negative marks to the buildings if these good features are not present. So that is how we list the building, create a rank system, and take the top ones which are the worst buildings and go ahead for the next. So this one code has already come out by CV 39, which tells you, this looks at all the critical aspects. And do a rapid visual survey. There's a form which is given in the code, which is, it can be updated quickly or can be updated based on the inputs that we get from the practicing engineers. But that basically code tells you how to do a post-earthquake safety assessment of building. After the earthquake, how do we look at the buildings? And it has covered 2 or 3 types of buildings which are commonly available in this country. Then you have a detailed qualitative assessment where we do, this is again qualitative, where we look at all the features in much more detail. There is a structural features and non-structural features, again life-threatening and economic. So these two go together. With life-threatening, if it is more, then you assign a larger negative marking. If it has economic loss, larger economic loss, larger negative mark basically. So that's how the ranking system is created. All the good and bad are compared with each other. Good is listed, compare it with the structure that you have. And we take guidance from existing document, past experience, past people who have worked in assessing buildings. And then you assign this factor for structural, non-structural. Once these are given, then you compare it with the best building and say this is the structural deficiencies that we have. So different types of buildings can be covered. It's houses, stone masonry houses, houses with stone or brick. Then there are some features in the building which could be bad. You list them down and give a negative mark to that. And Then in this there's a method called Delphi method, which basically tells you how to do this, and they have listed a lot of features which are good and bad features. So look at those features and identify the buildings which are marked. So here if you look at one of the examples which has a siting issue, which the entire house is on the ground floor, then this is the ideal condition. Then house is sloped ground with access to 2/3 of level, you assign a -5% mark to it. So good building compared with the existing building, and then you add all this mark and see what is the level of the building, and do this both for economic and life-threatening features. This is called the research Delphi method, which is more involved. The second method is the Delphi method. You talk to people who look at the building and assign a ranking to the building. And there's a mini Delphi method, which basically is used in that code that I showed you, where you look at the building, make estimates, talk to people, and then say that this is the condition of the building and this is the rank to assign to the building. Then we have preliminary quantitative assessment, where we say check for basic load configuration, X direction, Y direction, whether they are okay or not, check the design. Some examples are given here. One of the bridge which can be quickly checked for earthquake load that will come on that, and whether this bridge is okay or not. So some features that need to be connected, I will skim through this. Basically, if there's a bridge, you check in both the direction forces that are coming and check whether the seating, bearing, bolting connections for the bridge is okay or not. This is a picture from Uttarkashi earthquake, which the bridge had collapsed, and abutment collapse. Again, another picture. Here there's another picture which shows the shearing of the bearing. The bearing which was connected to the abutment and the bridge actually sheared off. A closer picture. So again, connections play a critical role in making the structures safe. So this example, look at bearings, look at bolting, look at seating, look at overall lateral capacities, and look at lateral restraints if there are any. This is an example for the bridge that is created. Then we have basic evaluation. Again, 3 features that we look at in this is the stiffness, minimum stiffness, configuration of this, minimum stiffness, minimum strength. This is the code level compliance that we are looking at. But very basic, we do linear analysis, check it with the design codes, and check it with the load and design strengths of the provision of the codal provision, and say whether the structure is okay or not. And based on that, you go yes or no, and then take the next step. Detailed qualitative assessment basically involves doing a detailed analysis and combined with the behavior of the structure. And when the behavior is good, all these 7 features have to come in the structure, which is configuration, stiffness, strength, ductility, along with deformability, good collapse mechanism, and energy absorption. So these 7 features, I'm sure you are now familiar with this. Even Rupen has showed this, and I have showed this at least 3 times in this presentation. So key aspects is this type of 4th level of analysis. 4th level of assessment will require some kind of nonlinear analysis, understanding of what are the behavior of nonlinear analysis. So if you look at detailed qualitative assessment, we have configuration, stiffness. Behavior wise, I'm showing you how it will show in a nonlinear analysis. Strength, ductility, deformation, and mechanism and energy absorption. So this is for an earthquake. If you're doing a back and forth loading, this is how the behavior, you would be able to visualize the behavior like this. In closing, we have different levels of assessments, 0, 1, 2, 3, 4, and very large stock of buildings will need the first, let's say 30 crore buildings in the country. Then second level will be required only 3 crores. The third level will be required for 30 lakhs, and 4th level is required for 3 lakhs. So that is the kind of effort. As you go down in the level of evaluation, number will come down obviously, but the effort increases. So that is the goal of this code. So right now we are in the mode of prescriptive. Our codes are very prescriptive. You do this, you will get this. Or we're not saying you will get this, but these are the good things to be done, and then you will achieve a good structure is the message. You have to move towards qualitative assessment, qualitative to quantitative. And the 4 parts of safety assessment are surveying. Basically, we have to understand, collect documents, understand what are the deficiencies, and be able to compare them with ideal structures. Then screening again, screening the process of doing a large stock of buildings, and step by step, if you have 5,000 buildings, you do 1,000 in first year and then 2,000 in second year. Then shortlisting of structures using detailed analysis, and then safety evaluation, which will be some kind of non-linear analysis. So again, looking at this chart again, you examine the documents as a beginning, inspect the structure. This is the same chart, is present in different way. If you come to a point where the extent of damage is so much, then you take a decision that you need to deconstruct and demolish the building. So that is the idea of revising this chart and showing it slightly different way. It involves a lot of estimation also. The cost is an important factor where you say whether the structure should be retrofitted or not, whether it is economical to retrofit the structure or not. But all structures cannot be demolished. So it's a balance that we have to play as structural engineers and maybe planners and designers, whether the structure can be demolished or it needs to repairs. So identify demolished deficiencies, decide the intervention, do again this economical evaluation, whether retrofit is possible, retrofit, not demolish. So both paths we are trying to say or provide in the course, so that the structural engineer is empowered with this, taking a decision either way, whether to demolish or not. Recommend, undertake the retrofit, and that's where you stop. And that's all I have. Thank you very much, and I'm grateful. I would like to apologize. Professor Murthy was supposed to be here, and Professor Murthy has also asked me to specifically apologize to all of you. I know you were expecting him, but for unfortunate reasons he's not here. But I hope, I'm sure it was not Professor Murthy, but I hope this was a little bit of information has been transferred for us. Thank you.
Thank you, Arleka sir. You have nicely explained assessing and retrofitting of the structures with nice illustrations and good pictures. And he has explained each and everything of the subject. So thank you very much, sir. The time is actually overrunning. So now, next subject is pre-draft of IS 456 by Professor Rupen Goswami sir. So I request Goswami sir to start with the presentation, please.
Between U and T, so will not take much time. Look, they've understood. They've given me warm water so that I don't bother you all too much. Okay, I guess this is also the moment, because IS 456 is something that is very close to all of us. I mean, right from this is the first love for any civil engineer, right? IS 456, and I have the responsibility of talking about that also. Okay, so let me begin. Very quickly, the first publication of IS 456 was in 1953, and we had working stress method. And I'm going to highlight few items just so that we understand the whole, sequence of things that are happening. It was for general building construction. It was stated. 57, we had the first revision, working stress method continued. 64, the scope was broadened to include, to make it applicable for all concrete structures. Okay, and then of course, what you see as M100 and 400 is not a typo. It was in the before the MKS or SI system. That is why it was written as M100 and 400. So basically 10 to 40 in today's context. But the important point is, as part of Appendix B, ultimate load method was introduced, and that is very important. And we had the introduction of the stress block that we know as of today. Okay, And if you see the stress block, it was 0.68 or whatever, we call it 0.67. That was the strength. Concrete ultimate strain capacity was 0.0035, which later was used in the 78 revision, which is the third revision, where we got our limit state method of design. And we continued with that same thing. So the first statement that I'm making today, which is a slide which will come at the end, is that today in 2024 as we stand, we are talking about structural design provisions which are 46 years old without any revision. So it's not just one generation, but multiple generations of engineers, we have been using the same design provisions. Another important aspect which was there in 1978 revision was this, requirement of design aids, and that is what we all know, SP16, SP, all these special publications. Very, very important. And why am I raising this issue? I'll tell at the end of this particular thing, right? And then, of course, this statement and attempt has been made to unify the approach of design of reinforced concrete and pre-stressed concrete, because this was foreseen in 1978, but we still had 456 for plain and reinforced concrete and structures, and then we had a separate standard for pre-stressed concrete. Today we are going to unify all three, and that is why I am showing all these important landmarks, so to speak, in the development of IS 456. But going back to the stress block, we basically took the ultimate stress block, again it used a partial safety factor of 1.5 and came down to this stress block that we use today for design of our structures. The 2000 revision, an important revision of IS 456, was important because for the first time the concept of durability came into in a big way, other than addition of or introduction of use of admixtures and so on and so forth. So basically we were moving from OPC to all the new cements and other materials that are coming in. But as far as structural provisions are concerned, we are still, there was only one change in structural design provision, that was of shear design clause. That too was in a little incomplete manner, but otherwise it was 2000 revision was primarily based for durability, right? We went with this, and the other aspect that happened was the concrete, look at this statement, for concrete of compressive strength greater than M55, design parameters given in the standard may not be applicable, was the statement written in that standard. But if we look at ourselves today, we have gone well past all this. So essentially we are designing, building and constructing structures without any standard. That's the reality. So this is where we are. We are now working for the 5th revision of IS 456. And let us see what it is going to bring us this time around. Also parallelly, we are working on the 3rd revision of IS 1343. It is going to be superseded because pre-stressed concrete is going to be subsumed within IS 456. So let's look at the overview of the things that are going to come. Scope of revision, as I said, it's going to be an unified code for plain, reinforced and pre-stressed concrete construction, right? And precast is obviously not going to be part of that. So that is it. What are going to be the contents of the new revised IS 456? We can call them chapters, sections, doesn't matter, but essentially there are going to be 11 of them. Other than scope, reference and all, basis of design, design loads, structural materials, structural analysis, structural design and detailing, construction, inspection, testing and monitoring, and dismantling and demolition. So these are going to be the main sections under which the whole content will be presented. Design loads, Arleker already showed. Essentially, there are two types of loading, force and displacement loading, and there are going to be 10 force loads: dead load, imposed load, wind, snow, water, earth, blast, impact, construction load, and pre-stressing, right? And 6 displacement load effects: temperature, creep, shrinkage, elastic shortening, foundation settlement, and earthquake, ground shaking effect. So essentially, when you say these are the 10 plus 6 loads, we will have load combinations also appropriately provided, which will have one or more of these different loads coming into the picture. What are the basis of design? So basically, a structure, a reinforced concrete structure, is going to be designed for 6 basic requirements. Obviously, the first is, when we talk about design and what is generally taught in colleges, is provide strength, right? PU, MU, VU, TU, all strength, 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 strength. So that is what we talk about in our design code. So obviously strength is going to be the most important quantity, but then there is going to be design for durability, and that's going to be a new thing coming up in this particular revision. Obviously, once these are done, then there will be check for serviceability, and then there are the new 3 terms that we need to get used to slowly, which are integrity, robustness, and restorability. And we'll see what each one of them are. So strength, I don't need to emphasize more. It's very fundamental to safety. So when you talk about strength and IS 456, particularly limit state design, as was introduced in the 1978 version, we actually had definition of strength based on 2 parameters, 2 quantities: axial load capacity, axial strength capacity, and flexural strength capacity, bending moment capacity, were defined based on strain, based on limiting strain values, whereas shear and torsional strength capacities were defined based on stress values, right? So we have tau C max, and so on and so forth for defining shear capacity. But when you talk about moment capacity, for instance, we talk about under reinforced, over reinforced, whether the concrete has reached its limiting strain or reinforcing steel in tension has reached limiting strain. So the definition is based on strain. Now the ideal situation would have been to now, after all these years, move totally to strain based definition. But we will not be able to do it even now because we do not have enough experimental data. So we'll continue with that. Serviceability, essentially, be it in terms of deflection, crack width calculation, or any other, vibration, acceleration levels, rotations, all these will continue to be carried out based on stress levels. So essentially what it means is that, and I'm going to say it explicitly, is that working stress method is going to stay. Okay? So engineering colleges have to go back and start teaching working stress method also, which we have stopped because we were told, limit state method of design is the best thing that has ever happened to mankind. Well, durability, in the previous presentation we have seen enough of bad situations. So here the idea is that there is going to be a part of design, and I'm going to talk about them, in terms of chlorination, carbonation, and sulfate attack. Also, the bigger challenge that we face today after 24 years, even if we can start from 2000, which is the last revision, we have an explosion of different materials and admixtures and mineral admixtures, chemical admixtures, and so many things, right? And that is really the challenge that we face problem of plenty, so to speak, in terms of handling durability, and that is why it's also taking a little while to finalize this as this part of the standard. And obviously we'll have prescriptive limits in terms of free water cement ratio, minimum cement content, and the usual things. So they are going to be there. Then we're going to talk about robustness, essentially under blast, impact, and fire. So here we need to ensure that a structure has adequate strength, plastic deformation capacity, and rotation capacity to take between these effects. Integrity, again, essentially it's talking about redundancy, alternate load path, and inelastic deformation capacity. And definitely we have a huge stock of existing structures that may warrant restorability. Essentially, they are losing their capacity because of natural deterioration, and in addition due to overloading due to any one or more of those 16 different load cases. So sometimes we need structure to be restored. So therefore we need these particular things to be taken into account. So to summarize all this, this is again a load deformation curve capacity that we should take back. This is something that I feel we should take back from these days' effort. So the first is strength, serviceability, durability will be there, an important part, and these are based on the force level calculations, right? Robustness is there, sitting there. Integrity is, it should not fall apart, the structure should not fall apart, and then restorability. So obviously what you can see is that if you leave durability aside just for a moment, strength and serviceability, linear elastic analysis, code-based design. So code comes in, gives you some force, gives you some ways to estimate strength, and you can be done with that. But the moment we start talking about robustness, integrity, and restorability, we have to get into understanding the actual nonlinear behavior of the structure. Now, this is where the whole challenge is. Do we have to do this for everything? So obviously no. So that's the sequence. If I have to put it, strength, serviceability, durability, and then robustness, integrity, and restorability. So these are the 6 items that we will have to think of as structural designers. Do you have to do it for everywhere, for every structure? The answer is no. Obviously, the first 3, strength, serviceability, and durability, are mandatory requirements for all structures, right? And only in special situations, special structures where the owner specify this as a requirement, robustness, integrity, and restorability will come into the picture. So don't, there's nothing to panic that it's not that our design will continue to be done the regular way for most structures, hopefully, right? So that is the thing that I have to say. So that's 1, 2, 3, and 4, 5, 6. So what are the major changes? So this is an important change, of course, conceptually this is how we have to look at the standard. What are the major changes? The first major change, why I mentioned about the chronology, was the grade of material. Remember M10 to M40, then M40 to 55, and then suddenly you can use anything higher. This may not be applicable, and we left it at that. The whole idea was to go all the way up to 100, but the fact remains that we do not have test data. We have test data for material test, but not even of structural member. Forget about structures, right? So the next proposal is to leave it up to M80, but even then we do not have test data. So the final conclusion may be, I'm not committing anything yet, to limit it to M60, till which point we have enough experimental data both from within the country and abroad, so that we can rely on it, right? So as engineers, as students of science, we depend on proven data, and that is what is available till M60. The debate is still on. But the interesting thing, if you are going to stay till M60, then there is no issue. But otherwise, the problem was that with high strength concrete, one of the key fallacies is that high strength concrete is very brittle. We say that, but essentially what it means is that the two limiting values of strain, 0.02 and 0.35, do not remain fixed. And the implication of that is that the ductility of members designed with high strength concrete is very less. And that is something that we have not been talking about, because until now our design was only based on strength. We never looked at deformation. We never cared about deformation. So long we provided adequate strength capacity, we thought it is perfect. So that is the change, fundamental change that may happen. Okay. So that is it. Reinforcing steel, again we have the same problem. Problem of plenty, because 415 steel is anyway unilaterally stopped. The 500 and 550 grades are basically the same steel, sold as whichever grade you like to purchase, right? And 600, 650, 700 and so on, we are going on adding to that list without doing any structural testing. So the bigger question that at hand is where to draw the line. But I'm sure all of you agree that there has to be a line drawn somewhere, because without testing, without knowing anything about how a structural member is going to behave, I think it's risky to allow. So that's where the issue is. With regard to durability, of course, mixing of different grades of steel has been proven to be detrimental for reinforced concrete structures, and that is something that probably will come in explicitly. There is another new concept which is doing the rounds, is about service life, and there's a proposal to allow designers to use design different structures for different service life. And this is where the durability design comes into the picture, and so that you as a designer can say, oh, this is my structure, and therefore I need not design it for 50 year or 75 year or whatever. I can design for So this concept is another new concept that's going to come. I do not have time to go into the details of it, but I'm just highlighting the major conceptual things that you should be looking forward to seeing in more detail in days to come. Exposure classes remain more or less the same: mild, moderate, severe, very severe, extreme. The definitions are rewritten a little bit here and there, and that is how they are going to be. This issue of service life is going to be controlled by three parameters primarily: chloride, carbonation, chlorination, carbonation, and then sulfate attack. And particularly with regard to carbonation and chloride attack, there is going to be calculation of cover, the minimum cover, based on your exposure conditions and so on. So that is where a little bit of change. Earlier it was all prescriptive, so to speak. Now, depending on what you want, you should be able to calculate what is the minimum cover that's going to be required. So that is the idea. Sulfate, again, because of lack of enough experimental data, it's probably going to be prescriptive still in terms of minimum grade of concrete, cementitious content, and so on and so forth, all these other parameters. Then IS 456, when we began working on this, there was this whole idea of, since it's going to be the unified code and it was under BIS, there was an initial discussion about 456 talking both about confined and unconfined concrete. Traditionally, only in CED 39 or earthquake engineering code, we talk about ductile detailing and confinement of concrete and so on and so forth. But since 456 is still going to be the mother code for design of concrete structures, it was felt that this concept should come in IS 456 directly, and not leave it for the earthquake codes 13920 to talk about it. So that is another kind of a change. Well, actually I don't see much of a change, because current 456 already talks about certain detailing which is intended towards providing a minimum confinement, but not explicitly quantified and so on and so forth. But anyway, that is something that is going to be there. So we are going to talk about cover concrete, distinguish between cover concrete and core concrete. The use of structural wall, very important. Again, IS 456 already had provisions for walls, and it's again going to reinforce on that and bring it very explicitly and forcefully this time. For instance, any wall, any member that has only one curtain of reinforcement will not be considered structural concrete. Because this is like that Mr. Asrani in that Sholay film, आधा इधर जाओ, आधा इधर जाओ, half of the cover concrete goes this way, half of the cover concrete goes this way, बाकी मेरे साथ आओ, कोई नहीं बचा नहीं. There is no core concrete left, right? So single curtain of reinforcement is like that. Okay, so this is something that is going to happen. These kind of members will not be treated as structural concrete, and therefore the intent is, what does it mean? Practically what does it mean? It means that these elements cannot be relied upon to carry primarily gravity. Gravity, well, they will still carry, but lateral load. And so you need to choose your structural elements accordingly. And it's for good reason. I mean, single curtain of reinforcement has shown poor behavior all through the history. Structural systems, this is where again lot of deliberations went on. Do we kind of talk about flat slab, precast, all these things? Because today what is happening is these things are not talked about. They're not part of the thing. I mean, flat slab is there, of course, but then they have become very major or very commonly used structural systems. So therefore, a need was felt to talk about them, give provisions, like what was done in IS 13920, IS 1893, in terms of buildings with flat slabs. So there were certain requirements in terms of more stiffness, limiting drifts, and so on and so forth. So here also similar things are going on, and we may see provisions for these in IS 456 also. Talking about post-tensioning and pre-tension, slabs. Again, there is a requirement in terms of minimum size of thickness, minimum size, minimum cover, and so on and so forth. So these things will come into the picture. Structural wall I have mentioned. So essentially, structural walls are, the idea is to say that although it is IS 456, but do not leave the entire safety related aspects due to earthquake, or lateral load, or blast, or because blast, impact, all are now coming under the purview of IS 456. So therefore, there is a need for IS 456 to talk about structural walls and make its use almost kind of mandatory in structures. Structural analysis design primarily will continue to stay based on linear elastic analysis. So all regular structures can be done, analyzed and designed the way we are doing currently, except for those special cases where we need to look at integrity and robustness. We may have to get into nonlinearness, and this is the departure. This is a significant change, an additional part that may come, because these are becoming important requirements for very strategic projects, and so we cannot do away with these kind of things today. explicit in terms of structural analysis, one of the key things that always happens is that, you know, this PT slab in as part of moment frame building, usually the building is designed by somebody, the PT portions are designed by somebody else, and they are just put together. And the point is, when the PT slabs are put and pre-stressing is done, we forget that the columns see additional movement. Right? Because it is done by somebody else, and I've personally seen situations where the columns do not have capacity, and then how do you salvage? So you start over all, you know, and even after, and the bigger problem is once the construction is done and when at a later stage all this is realized, then it's a mess. So we will see more explicit statements in terms of how to do structural analysis in such cases and so on and so forth. Okay, the most favorite topic of limit state design. Essentially, you know, as I said, strain limit based axial and bending moment capacity will continue to be there, and strength based shear force and torsional moment capacity will be provided. So that is what we are going to do, continue to do. But there is going to be a fundamental change here, and I want you know, all of you to pay attention to this. So when you talk about axial and bending for our regular load strength capacity calculation or even PM interaction you know, development, we talk about these limiting strains. So we have the limiting strain in steel 0.002 plus 0.87 Fy by ES, and for the limiting strain for concrete, let's say for flexural action is 0.0035. And so we draw the strain diagram, we write the corresponding, we draw the stress block, and then do equilibrium and find the strength capacity. Typically, what we see as MU, what is that U? We are still with the ultimate load method concept, and that is why we call ultimate moment capacity. It's not ultimate, we have already used factor of safety. It's not ultimate anymore, right? But we continue to use this ultimate word for the last 46 years. But that's okay. We can call anything, you know, by any name. The point is, it corresponds to the secondary compression failure or crushing of the concrete. That is the whole idea, that concrete strain ultimately reaches 0.0035. What happens is, if you look at smaller members like beams, columns in building systems, there is no issue with that. Okay? The strain, the maximum strain, tensile strain in steel will be reasonable. But when we try to apply that same formulation to structural walls, okay, you have a 2 meter, 3 meter wall, and if the extreme compression fiber has to reach a 0.0035 strain, the tensile strain on the other side has to reach such high value that you will necessarily have very large crack widths, and that's going to affect the durability and subsequently everything else, right? If this could happen, the fact remains that it never happens, and that is why even everything looks okay. But the implication of that is that we are overestimating the realizable moment capacity of walls by a margin of 30 to 40% by doing this. Okay? In case of smaller sections, this difference between where drilling happens to that secondary compression failure, the margin, if you do calculation, you will see 1%, 2%, 3%, 5%. Not a worry. But in large cross-sectional walls, this can be 30, 40% difference. And this is a significant thing. Also, this is not the, this can therefore, and this higher strength, in particularly in walls, is not realizable. Because for the wall to reach that state, the entire structure is going to get badly damaged, and you do not want that. So therefore, the definition of flexural strength is going to be revised to from the secondary compression failure fracture level to this level where yielding actually happens, and that level of curvature is consistent with the crack width that you would expect for regular durability over the design service life. So that is going to be a change in terms of how the strength capacity is calculated. Okay, so that is what you have to pay attention to or look forward to. Also, it essentially means that the level of curvature that you will see in these cross sections will be consistent, as I said. So that is there is no change as far as basic calculation is concerned, except that the definition of strength. So we are not going to use ultimate strength. We are not going to use PU, MU, VU, TU anymore. We are going to call limiting strength or design strength. These are just going to be called design strength. Okay, and that is what. So you will see new symbols with new, we'll stop using of these terminologies, this PU, VU, and all that. Working stress, of course, will be there. So this is what it is. Ultimate load method gave us capacity there. Working stress gives us capacity here. But we used a partial safety factor and continued to call that ultimate strength. It was never an ultimate strength. Right now, the proposal is to use a strength which is consistent with the durability that we expect over the stated service life. And that is what is the change in definition of strength that is going to happen. The eternal problem that we face is between the definition of what is a column and what is a wall. Right? So, and it's good to be in the no man's zone. So, I'll not say, but maybe some amount of policing is going to happen there. Watch out for that. But the more important thing, we want to raise here is that, see, whether a vertical member is a wall or a column is not so much dictated by the aspect ratio of that section, but in terms by its behavior. So if you do if you look at the bending moment diagram, if you look at the shear force diagram, you will see whether it is actually behaving like a flexural member or is it behaving as a shear critical member. And that is what is important for structural engineers to look for, and not play this trick of controlling everything by the aspect ratio of the thing. So something towards that you may expect to see coming up. Beam column joint, IS 13920 brought in a big way. It's also going to come into the regular design of IS 456. In terms of pre-stressed concrete, there's going to be, since it is going to come into IS 456, this was also used as an occasion to revise and improve that, because at the end of the day, if the definition of reinforced concrete member, flexural member strength is going to be updated, so needs to be done for pre-stressed concrete. But not just that, both for bonded and unbonded case, now there will be no approximate table-based strength calculation required. The pure mechanics-based using equilibrium, compatibility, and constitutive law, that whole process is now going to be given so that we follow a consistent method of calculation, which also can be programmed, in any spreadsheet or computer program or whatever, and all these expressions will be, provided. So that is that. Working stress method, of course, we can't do away with because we need to check that with deflection and all the other situations. So it will continue to be there. Although I, personally understood that probably there is some aversion towards using this word working stress method. We are good at finding way out. Detailing. This is not going to be allowed. In fact, even current one talks about 135 degree hook. It was. I don't know how it came into the being. Understanding that IS 456 doesn't talk about 135 degree hook. Only IS 13920 talk about ductile detailing. It was not the case. IS 456 did talk about it. But one change that's going to happen is that we are going to require one full complete hook for all members. particularly column sections. That is one thing that's going to be a requirement, and in addition to that, we can have cross ties, additional links, and so on and so forth. Spiral reinforcement is not helping. One hook alone is not going to provide neither the confinement nor your shear capacity. So this is another important thing, that all these members that we usually believe to be compression members actually also have to be designed for shear. And so that is something that will be stated explicitly. So only transverse reinforcements and individual hoops will be permitted, and of course with all the other requirements of detailing in terms of spacing, the hook length and so on and so forth will be there. The other important concept which was there but probably we never paid attention to is, of course once we talk about confinement, we are going to distinguish between confined and unconfined to an extent. But one important thing that we will explicitly talk about is this balance point, and essentially tension control failure versus compression control failure, which is very clearly which was given in, if you see all the charts in SP 16, if you remember all the radial lines, FYD is equal to, right? It was there, but we never talked about it very clearly, and so what happens is in our pursuit of making very slender members, particularly columns, we always had our design load combinations sitting high up on the PM interaction. All those are anyway sitting in the compression failure zone, so not good in terms of achieving ductile response. So that also is something that may come in. Well, open ground story, and then comes the different types of systems, structural systems. Some mention about some of these things. Precast buildings is something that we, of course, it will talk about design of these, but essentially, as individual components. But as a system, there has to be a separate standard talking about precast construction. That is something that needs to be developed in the country, because a precast member cast and fabricated is not a solution for, is not the complete solution, so to speak. So we need to have those things. And and then of course flat slabs, so we'll have provisions for these also. But the point is that a lot of these things have been going on in a very unregulated way. And so if you see the scope of IS 456 today in 2024, if all of these things have to be addressed in one go after 46 years, that itself became a very huge task. Obviously, when we try to do so much in one shot, there will be misses and there will be mistakes also probably, but an earnest effort has been put in. But I'm not claiming that it is going to be perfect. The bigger challenge was that civil engineering structures will always be, subjected to all these different elements of nature and different demands, and particularly and more so from different requirements that we set forward for ourselves, each passing decade, and keeping pace with that itself is a big challenge for IS 456. So, as I mentioned, these are the systems that need some attention. It's not clear as to exactly what to state and how to regulate them, but the discussion is still on, and in a way. We have already built many of these without any clauses, without any standard. Definitely the focus has been on use of these high strength materials, because this is the craze that appears to be unstoppable, right? Higher the strength is better seems to be the understanding, which is absolutely wrong. Sorry to say that, in the same breath, but no, I truly mean that. I truly mean that. We really do not need, for 99% of the structures that you build today, I mean, in the country, you do not need high strength materials. Let me be very honest about it. Yeah, for special situations, special cases, you may need, but for that, you need to do testing and be 100% sure about what you're doing and do that. Nobody is going to stop that. But for the 99% structures that you are building in the country, you really don't need, anything higher than what we have been already using. So yeah, so this whole discussion about, initially I said about 100 MPa is what was proposed. Then there was a discussion, no, we should allow up to 120, and then finally we realized that we don't have data even for 80. So that's the whole game that we are dealing with. Okay, so not just material test, because any material can be produced, and a standard can be created for that specification for consistent manufacturing of the material can be generated. But the use of that leading to a safe, sound structure, serviceable, sustainable structure is what needs to be proved, and that has not happened. The challenge is that it's not about the material and all, but our somehow we have also faltered in our basic design aspect also, and so we need to be little cautious, and also the standard has to have precautions to avoid such silly mistakes, and that is where we need to ensure that a certain basic safety is guaranteed, right? And that is where code compliance comes into the picture, and the earnest request of, attempt of ISSE 456 is to ensure that there is certain shade of safety that is embedded in all structures that we produce henceforth. As I mentioned in the morning, eventually the purpose is to have a closed loop process, because if we are going to assess integrity, robustness, right, we need to have this, and that is a culture, a tradition that slowly needs to develop, and nothing better than ISSE 456 should be the starting point for that. It's not going to happen overnight, we all know that, but then if we need education and practice to move towards that, 456 has to take the lead and start talking about it, if not recommending it. So that is very clear. The other aspect is that we do not seem to learn from our past mistakes. This is a photo I saw 21, 22 years back, and I was curious to know what is the story of this. This is a father and daughter rebuilding their house exactly the same bad way. The way it was built and the way because of which it collapsed. Right? We have to learn from our mistakes. And so, we need to look at what are our priorities. Well, safety, functionality and sustainability are three items that we cannot negotiate, cannot compromise today. In 2024, standing in 2024, we cannot afford to have any compromise on these three items. Between aesthetics and economy, there we can choose which one to give priority depending on what type of structures we are talking about. Right? And if this is a philosophy that we all agree to, then definitely there's a way forward to develop our standard and then improve our practice in days to come. So, to summarize, this is where we are. I mean, in terms of structural design provisions, we have not made any change in last 46 years. So yes, there's going to be some change. I've already highlighted the changes. Let us not be fearful of these changes. It's time we look at these changes and learn these changes and start practicing them. That's the only thing that we'll say. Demand, of course, there are also additional issues that are left in terms of, we are taught characteristic load, characteristic strength, but we are not sure whether the values given in 875 part 1 to 5 are characteristic or mean or what. You can go today and try and open those documents and try and read and find out. And if you find out, let me know what they are. So, and similarly, there are issues related to other aspects. So there are a lot of, what I'm trying to say is that it's not that ISSE 456 is going to solve all problems. It's not that ISSE 1893 is going to solve all problems. There are a whole lot of things that needs to be taken care of collectively, simultaneously, and then only we'll have a better, more systematic, environment for structural design and construction. So we need clarity. We need clarity on not just some of these specific items, but also on the philosophy of design per se. I say that. The good thing is that on a working day, when I see the hall full in evening, I see that none of us are actually spectators today. Most of us are actually playing the thing, and that's a good sign for the country. And with that positive note, I think we can conclude here, but not before highlighting that you are going to see a new look to ISSE 456. Okay, don't get frightened. It may look scary because there's going to be some 1400 pages to it. It's okay, we can do it. We can do it. If we are going to 46 years, we can do it. Okay? But more importantly, what I want to use this opportunity to appeal to is that bringing out the draft of ISSE 456 is only the beginning. We can even publish the code. We need good commentary. We need good design aids. We need solved examples. And most important of all, we need textbooks, so that the next and the next and the next generation of engineers learn the subject and then they start practicing properly. Right? On this point, I just will read out a message I received from BIS, from Mr. Arun Kumar, Head Civil Engineering Division. He says that Bureau of Indian Standards is pleased to bring out to your attention an exciting opportunity for preparation of reference handbooks on Indian standards. The Bureau has recently floated request for proposal for preparation of reference handbooks on Indian standards on the curricular areas identified for various disciplines, all that. The invitation to proposal is open to all organizations, institutions and individuals engaged in scientific and or academic activities and who qualify the eligibility criteria as mentioned in RFP. The point is, today we are hosted by ISSE. Right? It is organizations like this who should, in my opinion, come forward. People like all of you with so much of experience and expertise should come forward and help prepare the rest of the documents. Design aids, right? Solved examples. That will go a long way in reducing the anxiety level hearing that there's going to be 1,400 pages. So I thought I must use this opportunity to read out this message from BIS. All of us need to work collectively on this, right? So that is where we will achieve this mission of technical capacity development in the country. We need to develop these kind of design charts and design aids to help explain behavior, explain structural behavior, and make younger engineers understand structural design. These are sample calculations, sample charts to show where a section becomes under-reinforced, where a subsection becomes over-reinforced, where the minimum transverse reinforcement versus maximum transverse reinforcement, what does it cause to a structural member in shear, right? Classical example of PM interaction, tension failure zone versus compression controlled failure zone, and things like that, right? So we need lot of us to put in effort here, and Well, there are some major changes and many minor changes because we are doing it after a gap of almost 5 decades, and this is where professional societies need to come forward and help us all. I know you all are very busy, but this is the honest request that I can make from academia side. Okay? Do support, advise, assist, guide, help, and I'm sure occasions like this where all of us spend a day on trying to understand what is going on and why it is going on, will go a long way. We need to do this more often, more frequently at many more places, and we'll continue to do that. But we also seek full support from each and every one of you. This is the BISSE to CET 2 Canon 5, which made 3 working groups, and some of us were involved with that. We are grateful to the chairman and other members here. I'll stop here. Thank you so much. Thanks to ISSE, SEFI, and of course VJTI for all your support.
Thank you, Dr. Rupen Goswami, for the excellent presentations in the morning as well as in the afternoon, who enlightened us on the revisions of code and what is going to happen, so that we get some glimpses. Now we are running short on time, so I request all the delegates, we have a break for only 10 minutes, so please have a tea and immediately come back. We'll have the panel discussion on 16700. Please. So I request the panelists to come to the stage. Madam Alpha, Dr. Rupen Goswami, so I will just briefly introduce the panelists today. Alpha Sethi is Managing Director of EMS Consultants Private Limited. She is currently convener of Tall Building Subcommittee of CET 38, Bureau of Indian Standards. She has been seismic advisor and consultant to states of Gujarat, Maharashtra, Delhi, Jammu and Kashmir, and undertaken post-earthquake reconnaissance survey studies also. She is a founding trustee of Structural Engineering Forum of India, that is SEFI. So a lot of discussions are happening on this forum, you must be aware. You can join this forum, that is also free of cost. She has been involved in design of over 200 tall buildings and holds a postgraduate degree in structural engineering from University of California, Berkeley. Welcome, Alpha Madam. Introduction about our second panelist, Mr. Anil Hira. Anil's professional expertise is in tall building design and complex structures and architectural engineering, with particular interest in wind and seismic engineering and soil structure interaction. He has been involved in well over 150 tall towers, over 200 meters in height, including 80 towers, over 200 meters worldwide, including Australia, New Zealand, Southeast Asia, Middle East, and subcontinent including India. He is recognized as a world expert on the structural design of tall buildings. He is a very active member of CTVH also, and they are conducting good amount of workshops and seminars also for the fraternity and structural engineers. So with this, we will start the panel discussion on this code. All the panelists will express their views. And of course, Dr. Rupen Goswami is also there to assist us. You have heard him in the morning and afternoon session as well. We have one mic with the floor level. If you have written some questions, please pass it on to us. Or other panelists, they will express their views on the topic, and then we will take forward discussions. Just to start with some questions and all, I will just have 2 brief questions. One important thing that is expressed by all the designers is the IS code is telling us to do this, to do that, follow this, comply this and that, which is not in the hands of structural engineer all the time, because architect is a master. He makes the plan very, very complicated for us. Now to have the second mode of torsion or third mode of torsion, that is also very difficult to achieve and comply. So my question is, who will bail the cat? That is, I think someone has to answer that. Maybe we have to go to BIS to do something about that, because see, unless we have good configuration, we heard in all the morning lectures also, the configuration very, very critical, very, very important. And which, if you don't have any control over that, then naturally we are not able to design or build good structures. That is my perception. So on that, I think panelists can throw some light and what exactly we can do about it. And the second pertinent question is, suppose the building is not complying with the codal provision, that is called a code exceeding building. And there are, I think, certain guidelines and provisions, 1, 2, 3, 4, 5, 6 items. If it is not complying, then that goes to code exceeding structure, right? Then you have to go to maybe that expert review panel, committee and so on, and they may approve. But I don't know. If it is not passing the codal provision, then maybe you have to go to some other expert or maybe proof checking consultant we call it. But sometimes you are on this side of table, sometimes you are on that side of table. So you design, I approve, right? I approve, you design. That should not keep on happening. Because they are not, again, going to do some exclusive solution. I don't know how that is to be addressed. Suppose really there are some issues in certain building and structure, and really we know that it is code exceeding or whatever way it is. But how to have good structures in certain situations? Is there any guideline to do this due diligence and all? So that I think people are very eager to understand from this code committee also. So these are, I think, some of the starting points I am just throwing up for the discussions. Okay, over to Arpa madam.
Good evening. I know that it's a bit late. I think they're very important questions that Mr. Vadalkar has actually raised, and just indulge us a little bit. So before we start on those questions, I think Mr. Adin Hirao has a few points which he would like to talk about in response to what we all heard today. So over to you.
Thank you, Madam Alpha. Yeah, I thought I was a good student there, and I actually took some notes, and I sort of summarized 7 main points that, I think in my 45 years of practicing engineering, and I still practice engineering, I still design. In fact, that's all I do now, design complex projects. So there's some messages that I thought I'd like to just convey. I'm from that country that was on that slide that showed the peak acceleration at about 2.9, that little country that plays cricket and plays pretty good rugby, New Zealand. That's where I was born, bred and studied. And I studied under Park, Paulet and Priestley, and some of the elderly people here know that they're the gurus of seismic engineering. And I recall Tom Paulet. He never, well, we didn't have computers, so we never talked about elastic analyses or linear elastic or non-linear elastic, because we didn't have computers. We were still solving matrices, right, by hand. But they were leaders in earthquake engineering, and it was all about testing and ductility and energy dissipation and gut feeling, and how you still design, and we still design 20, 30-story buildings in that country where you got peak accelerations of over, I've forgotten the number now, 2.6 G or whatever it was. No buildings have collapsed in New Zealand in terms of tall buildings. So there's going to be an important message there that I want to talk about. And when you look at the world's seismic events, and when you look at the fatalities, doesn't matter whether it's in Gujarat, Japan, New Zealand, no tall buildings have collapsed. Well, not in New Zealand and not in Japan in terms of a collapse. Sure, they're damaged. And when you look at the fatalities, 95% of the fatalities, unfortunately, are within buildings that were non-engineered. No engineers involved. And we as an engineering profession, we have to deal with that. And so I think we spend far too much energy and dedication on buildings that normally don't fail, even if whether they've been designed correctly or they've been incorrectly designed. They tend to perform a lot better because of the fact that they're down the track in terms of the period, longer period, attract less load. It's the 1 or 2 story residential buildings, the 2 or 3 story shop fronts that fail and kill people. And I think we've got a bit of a responsibility there. The third point, the gap between academia, authorities, practicing engineers and technology is getting bigger and bigger, and that's a big concern. And that's because we don't talk to each other and we don't develop the regulations and the process together efficiently. I feel we're going backwards. The fourth point, the analytical tools. As I said, I was designing 40, 50 story buildings without a computer. Well, tell a lie, with a mainframe computer. Now I can design 100-story buildings, non-linear, 3-dimensional, the touch of a finger on my laptop, and the answers come out within minutes. The problem is that the tools are getting advanced, but the people that use the tools don't know how to use it and don't know garbage in, garbage out. And our focus and energy is far too much on the analyses and less on the details. And it's the detailing which is I think, where the focus should be in terms of our ultimate objective of safety and minimising fatalities. It's an art. The computer's just a tool. The art, and the art of engineering, I think that needs a little bit more experience, and it needs a little bit of interaction between people with experience and the people that are using the tools. There are far too many young engineers that probably want to get into management far too quickly without actually understanding engineering. We touched on what the missing loop in terms of monitoring and instrumentation to get more data. And I think that's a challenge for us as a profession because we've got lawyers and not many people that own buildings want other people monitoring their buildings, but that's a good excuse to take them to court when things don't go right. But I think that's a challenge for us as an industry. The next bit, we are all engineers here. Unfortunately, the outcome and the success of a building is multidisciplinary. And I think it's going to get more and more multidisciplinary. We ignore the architects, really. I don't like having ugly, structurally very safe buildings that are square columns on a 9 meter grid, weak column, weak beam, strong column. I understand all the concepts, but at the end, the success of a building is judged by the mums and dads. And we need to be conscious of that. And especially in the new world, where people are putting more and more focus on social sustainability, we want to be in an environment where we like where we are living. And I think that's going to be very important. Seventh point, my most important point, that no one touched on it. We as a profession are responsible for 40% of the carbon footprint as a construction industry. Not one person mentioned carbon footprint. Concrete and steel is responsible for 40% of the world's embodied carbon, right? And so there's a direct conflict. We don't want our buildings to be safer and safe. We want them to be exactly in compliance with whatever we develop. I'm assuming that all our buildings have been safe from the day one if it's been engineered, right? Now, 100 years later, with advanced tools and that, we should be thinking about optimizing our structures. They should be more slender, they should be optimal, they should be, attractive. And I think it's going to be very, very important that it's going to be minimum carbon footprint. And so we need to put that as a factor in codes in terms of measuring the carbon footprint. I think that's very, very important. And the last speaker, we spoke about the retrofitting and in terms of repairing, retrofitting. That is going to be the very, very important for our profession. We can't afford to just demolish and rebuild things. Retrofitting is going to be a big item in India because we just don't have the time and the money to replace everything. And so I think that's going to be a big future. So the other points about materials, yes, materials going to keep changing, and whether we like it or not, I think the construction industry globally has lagged behind. We only have to look at the motor car industry and look at what Elon Musk has done in the last 2 or 3 years. And to be honest, I'm a bit progressive that I see that when you look at all the pictures of the failures, they are the 2 or 3 story buildings. Well, I actually think that they're all going to be built in a factory in another 10, 20, 30 years. All our buildings are going to be built in a factory. Even in India, as the economy gets better and better, labour costs are going to be expensive. China, it's already expensive, and they're automating everything. India, where traditionally labour costs has been cheap, that's why we still talk about reinforced concrete. I think it's going to be all MMC, modern method of construction. In the next 20 years, 30 years, this country is going to see huge changes, and the younger engineers out there are going to be quite different to me. So they were just my thoughts. They're controversial, but they're my thoughts, and I think we can talk about tall buildings now. Thank you.
Thanks, Anil. I think Anil has reflected some of the comments I was hearing even at tea time. So I think he's speaking for quite a few of you over here. And I think it was important that those thoughts and those opinions were articulated. And I think, so we have, I think all of you know that the Civil Engineering Division, or CED, of Bureau of Indian Standards has lots of division CED 1, 2, 3, 4. So the earthquake codes come under CED 39. And special structures comes under CED 38. I'm serving as a chairperson for that since the past 1 year. And we have the privilege, and Anil Hira is also with me on that committee. We had the privilege of having an opportunity to come up with the first tall building concrete code, and then we've come up with a new revision. And really what is interesting, and I think this brings up or springs up a new point which is very relevant to all of you, that our CED 38.5, which is the tall building subcommittee, is essentially comprising of a majority of practicing engineers. And we have academia also, which kind of keeps us on track, in terms of looking at things in a more balanced way. But I think all of us also are very responsible engineers. So if any of you have had a chance, I think most of you have had a chance to look at IS 16700, you would see that it is written keeping the practicing structural engineer in mind, and also giving credence to her or his maturity, his understanding of how structures behave. This code is not meant to be a primer to how to look at tall buildings. It's meant for mature engineers who have some basic and fundamental understanding of structural behavior. And then we are kind of directing them that as far as tall buildings are concerned, here are some parameters. If you follow these parameters, we more or less know that the behavior of the structure is going to be acceptable. That does not mean that if you don't follow all of these parameters, your building is going to be unsafe. It does not mean that at all. It just means we don't really know how the structure is going to behave. Therefore, you need to do far more rigorous analysis. You need to have more eyes on the project, and that's why we have the engineering review panel. I think what Mr. Vedalkar said is very true, that if you just have a peer reviewer, it's like, I pat your back, you pat my back, right? And we're going to have a nice little cabal, and I'll peer review your project, you peer review mine, we're one happy family. So that's why what we had originally planned, which is a first of a kind, that the Bureau of Indian Standards code is telling the municipal authorities or the building authorities having jurisdiction, that please formulate this kind of a committee which has these skill sets and let them sit together and review projects which don't follow these prescriptive codes, prescriptive requirements of the code. Unfortunately, that has not happened. However, I think Mumbai has a high-rise committee, and there are, Navi Mumbai has it, and different Pune, so many other, Surat also has started having. So there are some towns and cities in India which have started at least having a high-rise committee, which is some kind of a consolation if till the time you have an ERP. Right, so I think that's a good way to go. I think when you heard this morning what Professor Goswami gave, that there's a possibility your force levels become 1.5 times, 1.8 times, 2 times, 2.5 times, 3 times. I think first of all I must congratulate Professor Goswami because he's the only professor who has come out and said it as it is. Because there are lots of people who are involved in that code committee, but nobody has been so upfront and said, look, this is going to be the effect, and this is what it is. I think for those of you who are, and as I think what Mr. Anil Hira said, and it's fairly evident to all of you, that in all the earthquakes you've seen starting from the 1980s, that's from when I have been watching earthquakes, and I'm going to take the 2001 Bhuj earthquake and the behavior of structures in Ahmedabad, which were 10 stories and 12 stories, as an aberration because they were semi-engineered, okay? They were not even fully designed for dead and live. Those of us who have analyzed those buildings know about it. So let's not look at those 10 and 12 story buildings which collapsed as an example that even tall buildings can fail. No, they were not designed for earthquake, that's a different thing, but they were not even designed for dead and live loads. So I think just again to underline what Mr. Hira said is that you have hardly seen across the world in any earthquake, tall buildings which have collapsed and lives have been lost. There have been some which have suffered some amount of damage. Some may have even suffered damage which may not be repairable, and that building may have had to come down. But there are a handful of such buildings. But we have looked at that, and in this new revision, what we did is we looked at, and I think some of you have heard me say this before, so pardon my repeating it, but we looked at 10 different codes from across the world, and we said, wait a minute, the empirical formula we have in 1893 code, it really is referring to buildings which are low height buildings. It really is not valid for tall buildings. So that is why, after looking at all these different codes across the world, we came up with this formula, this new equation, which we have incorporated in this revision. And I think that what is going to happen is, even though the IS 1893 with the revisions which will come, and the force levels of Mumbai also may go up by 40% or whatever, you may not, as far as tall buildings are concerned, see a very drastic increase in your base shear. I think that is one thing which is good for you. But I think as far as the shorter buildings are concerned, yes, buildings which are less than 50 meters, you are not allowed to use that particular codal formula, the codal equation which has been newly introduced. And you will see that 1893 with the new revision when it comes out will cause buildings to be designed for much higher force levels, and also you will have certain challenges in providing the stiffness required for the deformation limits that may come out. So it may be a challenge. I think when it comes, we will have to look at it. And of course, I think that the difference, I think Professor Goswami, that's something maybe you can answer, is that the divide between academia and industry is something which which needs to be kind of reduced, because most of the people sitting here, and even me for that example, we come across a lot of buildings, and I think even Dr. Aldekar also showed that buildings are falling down without any lateral load. I mean, there's no earthquake which has come or no such thing. They're just falling because of issues of corrosion, poor maintenance, of durability issues, right? And those maybe IS 456 may be looking at it, but are we looking at it in a sledgehammer kind of a way, or are we looking at it in a nuanced way? So that would be also something which people would be looking at. And the other thing which I think is a concern is that, I know that it's not a nice thing to say, but I think a lot of times the codes have to be followed by people who don't have too much representation in the code writing process. So how do you think we can remedy the situation?
Thank you. I don't think there is a gap between industry and academia. We are sitting next to each other. You called, I came. I mean, at least we can afford to have a laugh at the end of a long day. No, I understand what you are saying. So I'll first take it little professionally. So you are aware that at least in CD 39, what has changed in the recent past is that for every item we have a working group of 5 people, where there is mandatorily 2 from industry and 2 from academia, and the chair and the convener can be anybody, right? So it is a conscious effort that is being put in today. I agree that probably when you all started 30 years back, it was definitely not the case, and 30 years back, even when I started this journey about 10-12 years back, I was like the only one of my age sitting, and I'm only listening to 50, 60, and so on and so forth. So I was in my 30s sitting there and listening. So I can assure you that things are changing, and we will have lot more participation coming in years to come. I mean, I'm optimistic about that aspect at least. So that's the first thing that I would like to say. With regard to the seismic force issue, I think it is not exactly academic per se, for various reasons. Because this effort, I mean, you have been looking at it very closely. Of course, the difficulty here is that there is no answer or no benchmark that is available. You can test a number and say this is the correct number, because there is no such background to it, right? So we have to have some hypothesis, we have to follow standard procedures, and then keep on doing iterations, no, try this, try that, and all that, and it has taken 10-12 years. I mean, today, somewhere we have to trust ourselves, and when I say ourselves, it's not me who has done it. I have played no role in that hazard assessment, but I'm willing to trust my colleagues. And if I have not done it myself and come up with another answer to prove the other person wrong, then what option do I have other than to believe that that answer that has come out through a very systematic scientific process is correct, which has been overseen by so many people for so many years, right? So again, on that front also, I would say that let's accept that. Of course, when we accept the change, anything, when we start undertaking a change, there are going to be challenges, there are going to be uncomfortable, situations. I think we can overcome those also in the long run. With regard to structures, collapsing or getting into bad state, even forget about earthquake and everything. Yes, I strongly feel that is definitely a real issue in the country today, right? More than seismic safety, that itself is a real issue. The last meeting we were discussing quality control, quality assurance. I think that is a major issue today in construction, right? So we need to look at that. But that's one aspect of it. The other aspects also we have to. So there are multiple issues here, and we need to work on all these fronts equally. There is no one magic wand which is going to come and solve all the problem, and there is no one issue, if we fix, everything is going to get fixed. So that's the outlook I think that we can adopt today, and the only solution to this that I see is that we really need, and I mean it sincerely, we need a lot of participation from a lot of people. I mean, this is the only way we can move forward. About one very important aspect that Anilji mentioned is design using gut feeling. I mean, this is what, in my way, I say that as a structural engineer, you need to understand structural behavior. I think that is what you also intend to say. Your gut feeling tells you this is going to work, this is not going to work, this is how it's going to react to this situation. And that understanding, that development of that understanding is very, very fundamental. So here, I want to talk about these things. One is code compliance. Code compliance is for a large number of people, of engineers, who may not have still developed that understanding of structural behavior. It is for them to ensure that I do all these things. I've done this, I've done this, I've done this. It's not technology, it is technology. I've done this. Right? That is why we need codes, and that is why we need standards, because a lot more people are in that group because of various things, including how academia is going, running the country. What we are doing in academia, we have to accept that. Then, once you have done enough number of those technologies, then you start developing, and then you will start talking about, talking about good practices. Okay, code says this, but beyond that, I think we should also do this. Right? So good practices is where some experience, this kind of and the final level is actually safety. But the point is, the structural safety is a very absolute, very obscure, abstract kind of a concept. So to reach there, you have to go through these levels, and that is why we need standards to begin with, and they often need to be prescriptive also. So ISSE 16700 is a classic example where you don't expect a 18-year fresh graduate to come and design a 200-meter tall building. Allow that, right? And so they have come beyond code compliance and already have started understanding structural behavior and have developed a feel for good practice, what is to be done, what is not to be done. Right? And that is where this is the classic example, and that is where we are talking about so-called code accidents. Although there is a strong, belief that code should not talk about code accidents, then there is no need for a code, so to speak. But I guess it's a very, very important document. It's going to be the leader in many such things that may come up in future. So 16700 in that sense is a very important document from that point of view. However, for the rest, I believe we still haven't matured enough to get done with the so-called prescriptive standards that we need to follow in the country, because we need to grow in that. We need little more time for that. Yeah.
Should we open it to the House for questions? We are open to answering 16700 or anything for today.
One question regarding the clause of lateral drift.
Hello. Yeah, I have one question regarding lateral drifts. It says that for design earthquake force, the maximum interstory drift shall be h by 250. So when we say design earthquake code, first whether we have to use it scaled up earthquake force, like with the approximate formula, because I believe that it should not be, it should be unscaled, and whether it should be with factor of safety, because this design word is getting, there are a lot of peer reviewers, and this question comes up and pops up again and again.
Okay, so anything, I agree with you that maybe we could be a little bit more clear, and maybe there's ambiguity there, and we'll definitely review that, and we need to see that. But all issues which have to do with serviceability, we only take the serviceability levels, right? So there is no factors which are added to that, right? Now, all the serviceability issues as far as the seismic loads are concerned, for serviceability, there is no scaling. There is no scaling. Now, the reason is that when you are looking at serviceability, you are also looking at the natural period which is given based on the analysis, right? And always what happens is that the analysis will give you a much higher natural period, which means that your building is far more flexible, which means your deformations are much higher, right? So therefore, there is no requirement for any scaling. There is no requirement for scaling to the base shear, the empirical empirical formula derived base shear. And also it is a serviceability requirement, so there is no scaling for the limit factor. Yeah, so that's clear.
This question is regarding the use of different grades of concrete for columns and beams and slab. Now, the code, the way I read it, it seems that in the joints between beams and columns, it is permitted to use the 0.7 times the grade of column, and it is still safe. Now, if that is correct, then when the flexural check happens for the joint, what grade do I consider? The original column concrete grade of column or the concrete grade used in the beams?
Try to answer that. So you're talking about the column, when the column strength is greater than... Yeah. So for the joint, for the shear within the joint, you have to use what the concrete is in the joint, which is the slab concrete. Yeah. And we're in the instant where you increase to have a puddle strength between the, then you use that concrete strength.
So it's not so explicit, so people tend to actually put the missile of concrete and be done with that without actually doing it.
No, the reason you allow for the column, let's say as you said the column is M70 and you're using M50 in the joint. The reason we say that you can still continue to assume that the column can be designed only in M70 is because at the joint it has very, very high area of cross section, right? And it's only for the actual load, yeah. Not for shear. Not for shear.
Hello sir. Good evening. I really like the presentation of Professor Rupen Goswami. I have a question. In RC building, how do we determine the yield point in the load deformation curve?
You mean to say for a whole building?
Yes sir.
Okay. See, you will never get a idealized with an yield point kind of a thing. So you will get a nonlinear curve. If you do, for instance, what is known as pushover analysis, you will get a curvilinear thing. And then there are various strategies of idealizing it, and then you can definitely find out a representative yield for that. So there are multiple. You can consider the first yield anywhere in the building to represent the yield. You can even idealize the entire curve and get an idealized, elastoplastic or whatever curve, and then say, okay, this is my representative yield. So its point is primarily to understand where your damage initiation happens, how damage progression happens. If you are trying to estimate ductility capacity, then only you need this. Otherwise, for the rest of the thing, you don't need.
Actually, my question was about ductility only. So, yes. I am asking about the displacement ductility demand.
Yes.
So, it is the ratio between the maximum deformation divided by the yield displacement.
So, do not worry. There is enough uncertainty going to be there in your whole earthquake itself, and that's also allutoric type. So, even a small deviation or variation in your estimate of ductility capacity and precise, there is no precise yield point for a building, for a structure as such. These are all estimates, and even if you have a small variation in that, that's not going to affect the final outcome of your design or anything by that much, because the uncertainty associated with the earthquake is even higher, which we are not even looking at.
Okay, sir. Sir, my next question is about the size of the grid points you considered for the PSHA.
Oh, I believe that is 0.1 kilometer by 0.1 kilometer. Macro zonation, I know people have gone with 50, 100 by 100, 50 by 50, 10 by 10. I think here it was 100 meter by 100 meter, which is 0.1 kilometer by 0.1. And why? In fact, this reminds me that why it was so important, this study, is that it's not that you and I or anyone here, if we just wish, we can sit down and do. The supercomputer, the parallel computing facility of the institute had to be used on a full, continuous basis to do such analysis. So a humongous amount of work that had to be done. So it's not something that we will be able to do as a country even on a regular basis from here. So therefore, for the amount of effort that has gone into it, I think it is only appropriate that we respect that.
Sir, regarding that 100 meter by 100 meter grid you have taken, did you do any convergence analysis?
All those things were done.
Okay, sir.
I personally have not done that study, but I assure you that all the standard procedures were, followed, and there were review committees, and there were, there was a separate subcommittee of CD39 which oversaw everything, and very eminent people were part of it. So all those things are taken care of.
Sir, last question. Regarding the overstrength factor, you told, so it's the ratio of the maximum strength to the yield strength, or it is the ratio
to the design force.
Okay, so it is the maximum strength to the design.
So basically it is overstrength include, it is that.
In US code, it is actually the maximum strength to the yield strength.
I don't see. See, there are two ways this overstrength that we talk about is, one is that from the yield to the maximum strength is basically due to redundancy in the system. That is what it happens. And from the design force level to the yield is what is generally called as the overstrength part. The point is, if you idealize it as an elastoplastic, then that peak and the yield becomes same. Then what you are left with is only the overstrength. So together these two are collectively called as overstrength, and that is what we are representing here.
Okay, sir. Thank you.
I just wanted to make a comment on the hazard map. I mean, I've been in the committee and I have the highest regards for the map makers, if I may call them that. But I think all of us must understand that, as Professor Goswami showed, that actual data from earthquakes, we have very, very little, okay? And we've picked up 60,000 points, okay? So how do some of these points come? Because I've personally gone through it and I've seen that. So I saw one of those points in certain scripture, they have described that this event happened and the earth shook and this happened and that happened. So then the person who's read it says, okay, so it was an intensity of 8. So if it was an intensity of 8, then I will assume it's a magnitude of so and so. Now what happens across the world when they make these kinds of maps? What they do is they have somebody who prepares that and says that, this is what I interpreted. Then there's somebody who peer reviews it. Okay, so there's a lot of rigor. I mean, I think there used to be one, there is a project which is called a GEM project. I don't know if anybody of you know, it's called the Global Earthquake Model. And if you see the rigor, so they will, when they're looking at the Indian subcontinent, they don't have 60,000 points. Because when they are looking at the point, they want very robust points. So when you have points which have been picked up, which, it's my interpretation, if somebody has written this in some scripture, that this is this, whether I think the intensity of that was 8 or 7 or 6, is my personal interpretation. I'm just pointing this out to you because there is a lot of such. The science is not 2 + 2 = 4. Okay, it's a lot of history in it, it's an interpretation of history. So, to be fair, the people who prepare these kinds of documents do a lot of work. But in the end, history is his story. His is very, very important. And I think that's one of the reasons that all of us must look at these numbers, must look at these things, and also use one's judgment also. So the point which I'm trying to make, there's no doubt in my mind that if you're looking at the Himalayas and you're looking at the base of the Himalayas and you're seeing the thick alluvial belts over there and you're seeing the kind of amplification which can happen there, there's no doubt in my mind that, yes, things can happen in the northeast, it can happen in some parts of Kashmir, some parts of the base of the Himalayas. Then when you come down, we are in the Deccan Plateau. We are really in the Deccan Plateau, and sometimes, yes, we've had up to the maximum. We had a reservoir-induced earthquake in Koyana. But we are talking about the maximum. We are saying is about 6.6, 6.7. We are not looking at 7 and 8. So the difference, for example, if I'm looking at Ahmedabad, which is also in Zone 3, and I'm looking at Mumbai in Zone 3. I don't think those two zones are the same. I think that Ahmedabad, with the kind of soils which it has and the kind of, it's right there in front of us. 2001 is, everybody remembers that. So I think that there are issues which we must understand that even hazard maps are consensus documents. It's not like everybody agrees to the same thing. But this is the best estimate for everybody to be put together, right?
In fact, we had a situation where one event was actually changing the kind of hazard estimate that we had in a region close to Calcutta in West Bengal. And it was caused by one event. Eventually that was removed from the database, and then we got a much reasonable kind of a thing. So yes, these kind of things did happen along the course, and so that's why I'm saying, the uncertainties that are associated with these kind of work is huge, but this is the best that could have been done given whatever we have in terms of database and everything else.
Yeah, very warm good evening to everyone. And my question, after listening to from the way long this particular workshop, I have a multitude of questions rising in my mind regarding where we stand and all. So out of that, I'll try to speak my mind on a couple of commentary and a couple of questions I have in my mind. So commentary would be like, say, since this particular we are sitting at the juncture of the time wherein the paradigm shift is going to happen in the design approach by the structural design engineers. So what I see that there is an increase in the forces. So the increase in force will cause lead to increase in the sizes of the structural members. So what I see in the socio-economic arena is that whatever the real estate area is going to decrease in a carpet area because it increases the member sizes, and probably that may lead to certain kind of litigation to your neighborhood because we have very shortage of the land, and that may your increasing the size of the member may lead to little in the neighborhood because your the member is going into their area or something like that. So probably the real estate cost could grow, probably go high into this force. So this is what I see the larger impact of this code rather than very much focusing on the technical aspect of it. So this is my commentary, and my question would be like when we specify the cover to any structural members, typically what we do is that in the whole all structural members for us basically divided into categories of load bearing beams and foundations, and for these major three groups of structural items we specify the covers, but we never specify the covers for the internal members or the external members. So that would lead to greater durability for the structure as a whole. So what I would expect in the upcoming code is that the cover to concrete has to be incorporate kind of environment where that particular member is sitting in. So that has to be there. So whether upcoming code mentions this kind of what you can say cover to members based on where it is sitting in the structure rather than in general to overall. That is one of my question to the panel.
Thanks.
I think that's an important point, and there has been discussion on, in that regard. We need to distinguish between members, elements that are internal versus external. So that distinction is being made. Thanks.
So second, my second question would be that, say nowhere in the code, we mentioned that our structure is designed for so much of number of years, because what we talk about only is the number of return of period. Can we say that this particular structure is designed for say 475 number of years or only 50 years of years?
No, because there are two aspects to it. One is the service life, and that is basically fundamentally related to the durability aspect of it. So that's one part of it. And now from there we also then draw the conclusion. Therefore, and depending on what is the level of exceedance level, for instance, for wind, for earthquake, or any other natural event for that matter, what is it that is acceptable? We take that and say that, okay, therefore this is the return period. For instance, in all building code for wind calculation, there is it is clearly stated. What is that for serviceability check? What is the level of wind we consider, right? For design, for strength design, what is the thing? So that is what we do.
So design life is based on what is the return period for the wind kind of thing? And
no, design life is not based on that. Design life is fixed. Service life is determined. Durability design has to be done to ensure that the structure remains serviceable for that. And then correspondingly for the other natural events, there is a call that is taken as to what is that level of thing that we do, and we connect it to the design life and see what is the exceedance level, therefore we are accepting in design. If that numbers appears to be okay, then we go ahead with that.
I guess my questions are over. But what I see is that definitely the story, kind of will be paradigm shift, since we are looking these codes in 1400 pages, and after 40 years, it would give a lot of kind of anxiety as well as
No. We will do it. We will collectively do it. Don't get anxious. Don't get anxious.
I think here. While you are there, I wanted to take this opportunity to ask you. Monthly writing, but we want to restrict our stresses in columns
to 0.4 FCK so that it remains balanced section, because the compression increases, it will become brittle. So why that clause is not, why we are not indicating that to walls? Why it is restricted to only columns? Because what we see,
if I'm not mistaken, and somebody can correct me, I think this came in the amendment.
we know it was supposed to come. I was waiting for that amendment, but it has not come in latest amendment.
Everybody thinks it's not come?
No, it's not come.
It's
okay,
not come.
I think because I remember that we discussed it in the amendment.
Yeah, even I was waiting eagerly that it will come, because again I am saying.
Okay, so that's a gap, because I was so sure it is there, because I know that in my whenever all of us work, we make sure that it's also followed for walls. But good point, I remember.
Thank you, ma'am.
Not for eight stresses, it's for only compression.
Okay, we are coming to the end of this session. So I thank all the panelists. I think certain very critical points have been raised by Anil Hira. Durability, sustainability and carbon footprint. That is also very, very important in today's life for all design of structures, that we must emphasize. And one more point is very interesting, that gut feeling is I think most important. That is important by Dr. Goswami also. And there is no substitute to good engineering practices, of course. So unless you have proper design, proper planning, proper execution, you are not going to get this success. That is, I think, the bottom line of all this. So I thank all the panelists, Alpha Madam, Dr. Goswami, and I thank the other speaker in the morning session, Jaswant Arlekar also, who has helped us. Dr. Murthy couldn't come here to represent it on India. So thank you very much to all the speakers and dignitaries. I must thank Director VJTI for making this hall available to us. Strategy Department VJTI who helped us for the arrangement. Similarly,
I must thank all the staff of VJTI Auditorium catering who has given the excellent food, though we exceeded the capacity. So I must thank all the participants also for the overwhelming response, because the registration has crossed 200 mark because the capacity of 200. So I thank you all. I thank all my colleagues in ISSE trustees, the sponsors, Ultratech Cement, who has sponsored the event, and they are always helping us in conducting the event. So thank you, Ultratech. And again, I thank all the delegates who has come from long distances to attend this workshop, especially on the working day. And till evening 6 o'clock, the auditorium is full, so I am very happy about that. So I again urge, if you are not member, please become our member, support ISSE and support the fraternity. As said by Dr. Goswami, we have to come together, and then only we can evolve good engineering practices, good structures, good codes and good structures. Okay, thank you very much.
रेडी सर को होना चाहिए था, सर को होना चाहिए था, आज क्वेश्चन होगा